characterization.
Since you're going to say something interesting, we started the recording.
Keep going, please.
Keep going. Andres?
Yes.
So, so where are you from? Say that part again.
Well, I am from Colombia. I am based in Bogota.
Wow.
Yeah.
So yes, and this issue with this lead poisoning has been quite a mess, because we have a social conflict. So also drug the dealers and other stuff went through illegal mining as a supplementary economical activity, and they just dumped massive amounts of mercury on our rivers.
That's shocking. And has any action been taken against that at all? Or are people just trying to pick up the pieces and try and resolve the issue themselves?
Well, to be true, it's quite a mess. Sometimes it goes into the news, then interest fades, and you go into that. And yes,
it's very difficult when it's not in the public eye to be able to get the awareness and the funding to be able to deal with it, I suppose.
All right, it's quite, to be true, it's quite a mess, and still there are some gaps, because the worrying thing is that they have been able to trace this stuff on the sea, which is quite, which you take into account that mercury usually stays close to the source. Having them so widespread is
it's a disaster, you know. Yeah, no, that's really quite concerning. But so no actions have been taken today to try and get them to reduce their operations, or
well, as I told you, it's an issue that goes on and off.
Yeah.
So it's also the other issue. Well, that has been solved, but it maybe is also quite interesting for you and maybe further research proposals, is that we used to dump a lot of Roundup,
sorry, there's a bit of reverberation there. Sorry about that.
The coca growth.
Yeah.
So we dump that on a massive scale from the air using small planes. Now this practice is forbidden. Some people want to put it back on, but yes, we are talking about dispersing this Roundup herbicide on a large scale.
Okay. Yeah. Well, I think that would be a really interesting thing to talk about in the open discussion, try and get everyone's feedback on how they could potentially deal with those sorts of things, for sure. So we're going to be starting in a couple of minutes. Is Scott and Ricardo, are you both there at the same time?
Yeah, we
I don't know whether Ricardo joined in and then caused a bit of a reverberation mess for a second, right? Hi, Ricardo. Great to meet you.
Hi, Francis. I don't know if you can see
Hi.
me. Nice
Yeah, I can see you. I can see you. Lovely to meet you. I hope you're enjoying your stay in Liverpool.
Yeah, for sure.
Sorry I can't be there in person to kind of show you around and see you in person, really. So Scott, I think we're almost ready to go.
Okay.
So if you want to start in a minute, and then just introduce Jeff after you're finished, and we'll just start the Ecotoxicology Symposium.
Okay. Shall we wait a minute or no?
It's 10 o'clock now,
Okay.
so yeah, we're ready to go.
So I apologize for my appearance if you can see me, but so welcome to the inaugural event for the environmental engineering interest group, sponsored by the Risk Institute here at the University of Liverpool, on ecotoxicology. The engineering interest group is brand new, and we're interested in teaching environmental engineering. We're interested in research, and we're interested in some outreach too, but we don't know what we're doing. We'd like you to come and join us and help us create environmental engineering at Liverpool. It's not like it's not here already, but it's sort of scattered. We'd like to integrate some of that. Today's event is going to be basically 4 talks by Jeffrey Dombacher, who will come in a few moments, and Ricardo Cesar. Jeffrey's from Australia, well, originally an American, but now from Australia, from CSIRO, and Ricardo Cesar is from Brazil. Both, would you both call yourselves ecotoxicologists?
Yes.
Jeffrey, you're an ecotoxicologist, right? You're really a more general modeler guy, but all of us have an abiding interest in ecotoxicology, and we're a little bit confused because it used to be 20 years ago that ecotox was hugely popular. Well, everybody was doing ecotoxicology. When you go to meetings like CTAC, it would have multiple thousands of people in attendance, and it was all the rage. That may have been because there was a lot of money at the time. The Superfund sites were working, and there was a lot of money in the United States, at least, for work in this area. There were a lot of Superfund contamination sites that needed to be cleaned up. But over the last 2 decades, people, I don't know if they finished their work and they cleaned up all the sites, or somehow the bandwidth of attention to environmental problems got diverted from ecotoxicology and contamination problems to more desperate problems like global warming and extinction, massive extinction, and loss of ecosystem services. Maybe we've been diverted in our attention, but it seems to me, and maybe you guys can correct me, but it seems to me that we've maybe lost focus is the right phrase, because it seems like there's less attention to these areas now. And it's not because, as I think Jeffrey would agree, that we've fixed the problem exactly. It's, things have certainly gotten better since the bad old days when the Cuyahoga River caught fire because of the contamination. But it's not like it's not like we've fixed all the contamination in the world. And especially in and the reason this symposium is held now is because we're working on a project with Ricardo and his colleagues in Brazil on mine tailings, right? Basically the contaminants from mine tailings in some very high profile dams that were created with mining operations that have failed and spread the tailings and the contaminants far and wide. And that's a general question. How do we deal with that? And so Ricardo is visiting here from Brazil under that project. I guess without further ado, I should introduce Jeffrey Dombacher, who's an old friend. We never met when you were in America, right, Jeff? But I knew you just from CSIRO, and I was very confused. He was the oddest Australian because he didn't really talk like the others. He's originally an ecologist, I guess, aquatic, riverine fishes. Well, his bio is displayed here. It says, a desire to understand the complex relations of fish communities, and specifically the qualitative nature of those interactions in fish assemblages. He's been working for many years now with CSIRO in Australia, monitoring and managing the ecological systems like the Great Barrier Reef, the marine ecosystems, the exclusion. I guess they're called, what are they called, Jeff? The marine fisheries protection zones or something. There's some special name for them that are very important.
Yeah, marine protected areas.
Yeah, marine protected areas, thanks. And he's, his title today is Addressing Complexity and Feedbacks in Ecological Risk Assessment for Rehabilitation of a Mine Site near a World Heritage Site. 2 sites in one title. That's a...
Yeah, that's an embarrassment, but that's what's going into the journal article. So
Thanks. So Jeff, I'll stop sharing and let you share your screen.
okay.
I'll also mute ourselves, but we'll interject if you say some outrageous something too outrageous.
Okay. Now let's just see if I can get all this technology right. Okay.
Yeah,
Yeah.
we can see that perfectly.
Okay. All right, so here we go. So yeah, my name is Jeffrey Dombacher. I've been in Australia now for 20 years. Before that, I had the distinct pleasure of running around Oregon chasing fish and trying to make the world safe for salmon. But then I got captivated by a theoretical tool called qualitative modeling or qualitative mathematics that grabbed my brain and wouldn't let it go. And because of that, I got asked to come down and work in Australia with the CSIRO. And that's been just a lot of adventure and fun. I get to meet all these interesting people like Scott Fearson. And yeah, and so one of the projects I've recently worked on, it's just coming now after many years, getting into a journal, hopefully. It's about rehabilitating one of the world's most productive uranium mines. In fact, most of the uranium that was going into Japan's economy came from Australia. A lot of it, most of it from this mine in Kakadu, the Ranger mine site. But now it's been fully excavated, and now they're decommissioning it. And because it's in the middle of a World Heritage Area, they're obligated to turn it back into natural conditions as they can, as much natural condition as they can. And they need to respect the wishes of their Aboriginal community that's been there for 60,000 years. So it's a very high profile risk assessment for a very complicated problem. They called CSIRO in about halfway through it and said, we need a little help with the complexity part of things. So that's where my skills got brought into it, but there's been other people working on it as well. Oh, so I want to acknowledge my co-author, Andrew Harford. He's with the supervising scientist branch of the Australian government that overlooks the research into the risk assessment work in Kakadu National Park. So this, the Ranger mine is set within the Alligator Rivers region. Let's see if I can get this marker here. Yeah, so the Ranger mine is here. And there's a big Aboriginal community here at Jabiru, and the Darwin, one of the bigger cities up in the Northern Territory, is just outside of this box here. So this is a vast network of wetlands that are connected. They have freshwater crocodiles and saltwater crocodiles. It's about 30,000 kilometers squared. It has a wet and season and a dry monsoonal season as well, with 1 to 2 meters of rain received between December and April. Has fantastic electrical storms, as you can see here. And the Aboriginal community has been here for over 50 to 60,000 years, and you can see the rock art here just next to the Ranger mine of their some of them totems here. I think this is a turtle here. It's a Ramsar wetland site. It's just amazingly beautiful. If anybody saw Crocodile Dundee, that's where he stood on the rock and swung that bull roar. It was right on that rock there. So it's iconic, central to Australia's heritage, and it's got lots of values. So the Ranger uranium mine is right here. It used to be known to the Aboriginals not to go there because people would get sick if they stood in this area. It had that much uranium near the surface that it could give off, a sickening dose. It was discovered in the early 1970s, and there was a mining lease started in 1979. It ceased in 2012. They excavated all of the milling ore and have been processing it methodically on site, and that ceased in 2021. In scheduling, it's going to be ending in 2026, and they're supposed to have the mine site rehabilitated back to equivalent to natural conditions. There's going to be lots of issues with treating the processed water that had brine concentration in it. They have to deal with the backfill pits and the deposits of tailings and brines into those pits. And they have to cap it all off and revegetate it. And so there's a risk assessment about that decommissioning and rehabilitation phase that the supervising scientist's office got called in to manage, so that it was done responsibly. And what's holding this whole thing hostage, so to speak, is I don't know how many millions and millions of dollars that are held in trust from the mining companies, that they have to do this rehabilitation to a good standard, or they don't get their deposit back. So that's why there's a lot of interest in getting it done right. So it was assessed that the risk assessment had some key knowledge needs. That was to determine if the key offsite and onsite risks associated with the decommissioning and post-decommissioning phases were viable and could be accomplished. So there was a need to inform. I mean, there's been research going on through the whole thing, but also future research programs in perpetuity until the thing is completely put to bed. That needs to be done to ensure the rehabilitation and protection of the environment. So they have had, as you would imagine, numerous expert elicitation workshops since this whole thing was kickstarted. It's been relying heavily on conceptual models and classic risk screening techniques and identification of key knowledge needs. So basically, if this is just a conceptual drawing, but there's this pit here, they have to then put the tailings back into it. And importantly, they have to reconstruct the 3D topographic surface and get it revegetated with a tropical savanna vegetation that is believably similar to the adjacent tropical savanna vegetation. They also have water running off into the adjacent Magella Creek, which has large value, or many greatly appreciated values, aquatic ecosystem values and cultural values associated with the waterway that runs next to the Ranger mine site here, right along here, Magella Creek. So they've done some classic just cause effect or pathway analysis of conceptual models of sources of risk, the stressor pathway, measurement endpoint, assessment endpoint to meet management goals. They've done this in spades. So they believe they understand these, the reductionistic view of this quite well. They understood that beyond that, they need a cumulative ecological risk assessment. This was raised by the Technical Science Committee for the Alligator River region. They wanted to make sure that ecological risks were considered not in isolation, but that they consider interactions between the different conceptual models that were developed. And they wanted to make sure that low risks wouldn't then have a cumulative effect that were greater than they were individually. And so they identified the need to do a cumulative risk assessment. And that's when they asked CSRO to come in, and I worked with a group led by Keith Hayes. We invited Scott Fearson to it, must have been over 15 years ago, I think, to give us advice about how to do that. And we've been going forth in those years, developing our ideas and applying them across Australia. And one of the simplest ways to show how we try to deconstruct problems and bring our different analytical tools into it is this picture here, which we find quite useful to helping people understand the different levels of complexity and the cause-effect relationship of your problem. If you have a pressure affecting the system, and there's some system variable that it gets affected by it, and there's some indicator variable or measurement endpoint at the end. Now, if the pressure and the indicator are the same, then you're great. That's a very simple problem. Like, you shouldn't have cyanide in your drinking water because people get hurt. So the pressure becomes the indicator. you don't need a lot of complex modeling. You just go out and need to measure it. And the way to conceptualize the problem is very simple. You can do that with unstructured lists or objective indicator matrices. But if the pressure then is affecting some other variable that becomes the indicator, then you might need something a little more complicated than just those unstructured lists. And you might go into structured lists, value impact matrices, all the way up to some statistical model to help you understand the correlation strengths of what you need to be measuring. If you have then directed feedbacks, where you have a pressure with one or more intervening variables that then gets to your indicator variable, then these simple unstructured lists and simple matrices are no longer fit for purpose. And you need to extend yourself into the more complicated approaches to understand the cause-effect relationships in the system. Once you start getting diffuse feedbacks going through many variables in cause-effect relationships, then you pretty much need you're into the mathematical realm of causation, or at least good statistical measurements to tease things apart. Then once you get feedback processes, the statistical methods are challenged. They're barely workable unless you have a lot of data. You then must concede that you need process models, most likely. And here I make the distinction between qualitative process models or quantitative process models. A little more about that later. But we use this screening tool to understand what methods we need to be using in ecosystem assessments of risk and applying the proper tools in the right spot. So for the work at the Ranger Uranium mine, we decided that we had feedback systems with sufficient complexity that we needed to embark upon process models. And because we didn't have enough data on the parameter strengths of the interactions between the variables in the ecosystem, we settled upon a qualitative approach that I'll explain to you in the next slide. So here we use qualitative mathematical models and their analyses. This is a one-slide presentation for the complete methodology of qualitative modeling. It would fill, of course, a book, but I'm just going to give you the overview from space, so to speak, of what the technique entails. So what it is, it's a causal modeling that has these what are called sign-directed graphs or sign digraphs. And you have system variables. These could be like grass, rabbits, and foxes, or I guess it wouldn't be grass and rabbits. It would be weeds and grasses and cows, let's say. And these variables here both have a negative effect on each other. So you have a link going from one variable to the other. From y on x, that's a negative link that has a filled circle. And this is competition between two variables in a system. And then y has a positive effect on z. This could be a predator-prey relationship where z imparts a rate of consumption or mortality to the y variable, and the y variable gives the z variable a rate of birth or growth. And based upon this simple display of cause-effect with the processes of biological growth or death, you can describe whole systems. And you can do it in the sign-directed graph form, or you could put it into a matrix algebra form. These are equivalent ways of depicting the same information. The negative competition between x and y is shown here by these two interaction coefficients, y on x and x on y. So that's competition. The predator-prey, this plus minus, is shown here between z on y and y on z. Okay, so these are equivalent representations of an ecosystem, right? And it only took a second to draw and to put up on a whiteboard to a room full of experts to say, is this how the world works? Yes, you can draw this sign-directed graph. We have these other interactions that are called modified interactions, where variable x doesn't participate, say, directly with y and z, but instead accelerates or enhances the strength by which these two variables interact. An example of that would be vegetation that a predator hides behind to be more efficient at capturing prey. And if that is the case, then you can create this new sign-directed graph based upon this depiction here, where that positive times that positive gives you a positive link from X to Y, Z, and then that positive times that negative gives you this negative link from X to Y. These modified interactions show up all over the place in ecosystems, and this simple depiction allows us to formally record them and analyze them in a very rigorous manner. So once you've drawn the system, then you get to understand its general feedback dynamics. Here we have, from the example above, X and Y gives you competition, and Y and Z gives you predation. Based upon these dynamics, you can understand whether or not the system has the ability to be globally stable, like the predation example, or locally stable underneath some constraint parameter space by which X and Y can coexist successfully. So you understand concepts of stability based upon the structure of the ecosystem, either with respect to the sign-directed graph or the matrix formulation. Either of them can be used to calculate potential for Lyapunov stability. As engineers, you should be familiar with those, with that terminology. So you can do a qualitative analysis of the potential for Lyapunov stability based upon the sign-directed graphs or the interaction matrices that you see here. You can also understand shifts in equilibria. So let's just say that there's a sustained increase to something that favors X, say fertilization or feeding of X. That leads to an increase in the population growth rate of X. You can then predict what's going to happen down the system. And based upon the sign structure of the system, you can say without fail that there's going to be a decrease in abundance to both Y and Z or Z. You can also, besides change in abundance, predict shifts in life expectancy. How this is based on the turnover rates of the system, of the variables within the system. So from this input to X, you're going to have no change in the life expectancy of Y, but you're going to have a longer lived population, older individuals on average in the population of Z. And this is based purely on the sign structure of the system, has nothing to do with parameter strength. Parameter strength on top of that will just enhance these or subtract from that general statement, but not only qualitatively, the system will show these shifts, either increase or decrease in these different metrics. And for the other system over here, given that there's a modified interaction, the same input to X leads to a shift in life expectancy of Y, whereas before there was no shift. And for Z, there is an ambiguous change because the system shows that could be either an increase or decrease in life expectancy for Z because of the sign structure of the system. So it shows you where you can and cannot make good predictions in the system. So if you're going to pick an indicator variable to monitor in the system based on life expectancy, you would not choose variable Z because you have a poor chance of predicting it because it has an ambiguity and it's based upon the community structure. Whereas Y will faithfully always give you a decrease or excuse me, no change in life expectancy, whereas this would have that one would have a decrease. So based upon the sign structure of the system, you can identify changes in abundance and life expectancy, and these can then be identify informative indicator variables. If you have a system that's being pounded by stochastic input, and the system is fluctuating between upper and lower bounds, then you can use time averaging as a qualitative technique. We have the expectancy of the variable of interest, where over a long time period, it should have an expected change of 0, but the variance should be greater than 0, it should have a positive variance. And under those conditions, then you can make assertions about covariance between variables. No longer can we predict whether X will increase or decrease, but we can with certainty predict whether X and Y will vary together or oppositely. So because of the sign structure of this system, if X is stochastically forced, then X and Y will have a negative covariance in their statistical structure, correlation structures, whereas Y and Z will have a positive covariance. So qualitative modeling doesn't tell you the magnitude of these changes, only the directional, only the directions of these changes. So it lacks precision, but you gain generality and reality, because you can put all of the processes that you understand to be operating in this system, either rates of birth or death, or modifications or enhancements of interactions. All of these processes can be used to then make qualitative predictions about shifts in abundance or life expectancy and stability. And here in this system, if you have a stochastic input to the birth rate, you cannot recover very much information because there's going to be an ambiguous covariance between these two. So you know it's not worth making an assertion about their changes based upon the sign structure of the system. So armed with these tools, we can go forth and try to map out the cause-effect relationships of a complex system and make identification of hopefully informative indicator variables and predictions about how management actions can be expected to affect the system. And these are some of the core needs for a monitoring program and a risk assessment program. So we applied these tools to the terrestrial and aquatic ecosystems that were impacted by the Ranger uranium mine decommissioning. Here's the Ranger uranium mine, a little closer up. There's some vegetation there's some areas of the mine that have been capped over with soil as a test to prepare for research programs, where they're looking now for, I think it's been going for 20 years, at the success of the revegetation, given differences in soil structure, grain size of the soil, slope, permeability. All of these things they're measuring as they make different test sites with different ways of configuring the mine tailings to see if it makes an effect on the recovery of the terrestrial vegetation. They're also doing a lot of water quality monitoring in the Malaga Creek that runs in a spot nearby, and with a keen eye towards the key cultural values, especially of crocodiles and fish and turtles, which have both food value and spiritual cultural value. So things that might get in the way of a successful rehabilitation of the mine site are well known. They have all of these external drivers, extreme events, cyclones, vast differences in rainfall with dry seasons and wet seasons and temperatures. There can be many different risks coming from the landscape. Fire is a well-known dynamic in the system that has, that's the chief disturbance dynamic of the terrestrial vegetation, but also there's the introduction of weeds, which we'll get into further, and feral animals like pigs and water buffalo can be very destructive to the vegetation and can completely destroy the horticultural efforts of the decommissioning work. There's also a lot of chemicals or nutrient solutes being derived from the exposed soils that are then leached into the groundwater and surface waters. And so these erosion components need to be thought of what's going to happen to them downstream in the catchment. So initially, when we did this risk assessment, we focused on a number of critical post-decommissioning risks, and we developed these qualitative models to identify processes that could lead to key uncertainties in the system that would need to be quantified and good indicators for monitoring, as well as testing whether management actions would likely or not likely be efficacious. So the first thing I do is when I get a room full of experts, and here we had about 20 experts from the scientists working for the government, but also scientists working for the mining company that are trying to rehabilitate the mine site. How do you think the world works? And this, while it might look messy, is actually moderately messy, I might say. It was a moderate level of complexity. This was, and I'm not going to go into showing you exactly what everything means here, but for instance, we have evergreen trees, and we have deciduous trees and shrubs. We have perennial grasses, annual grasses, perennial shrubs, and annual forbs. We have all of the fears of the biologist with pigs and buffaloes and fire frequency here. The difference is that the waste rock or the surface roughness might affect the soil and how that might affect the forbs and grasses. All of this was together in one model with the sign-directed graph. But what we found was that, and you'll find this whenever you talk to a room full of experts, people that spend their whole life studying one taxonomic group, sure as hell want to see it up in the model and make sure it's represented, because they believe that's one of the most important things in the whole model must be the things they're working on. And they want to see that high level of resolution, because more reality must be better, so to speak. More resolution of variables must be better. So when we did that, I often get this when I do these models. I concede to the group and I put up everything that they want to have in the model, and it leads to a large complex model. But then it leads to sometimes here are functionally redundant variables with respect to key ecological processes. Now, this resulted in numerous positive feedback cycles that masked core dynamics involving fire, competition for water and by the roots of the different vegetation components, and shade, the effects of shade. Also, fire frequency was considered in the workshop, the first workshop, but we found later that intensity was to be more important, and it misrepresented important dynamics based on frequency. So when we did qualitative predictions of this model and then tested them, confronted them with known dynamics of the system, so that if you have more or less water or more or less weeds, I would make a set of predictions from this model and then match it with the known results of experiments, and found this model behaved quite poorly. It was a very, very poor descriptor of known ecosystem dynamics. So then I went back to the drawing board with just a few key biologists and reconstructed the system, simplified it. And this is where sort of the art of modeling comes in, but it's not really art as much as just paying attention to key dynamics with respect to function and not taxon. And so we decided that tall grasses could be synonymized with anything, whether it be weeds or native grasses, that would have a direct influence, positive influence on fire intensity. Now, fire intensity would diminish the store of fuels held with the tall grasses. So there's a predator-prey type relationship. Fuel, fire consumes fuel, so that's a negative feedback. Fire intensity, when it's hot enough, will kill evergreen trees. Evergreen trees compete with tall grasses when they're young and moderate in age. Juvenile and young evergreen trees can be outcompeted by the root systems of tall grasses. So that's a competition for soil moisture there. Trees create shade. Shade suppresses tall grasses and short grasses and forbs. Tall grasses also suppress short grasses and forbs. Now, this simple model held all of the functional complexity of this model with only 5 variables. And when we did a test of it and confronted it with the known dynamics, we said, if you have an increase to weeds and you make an opposite, and this is putting the predictions within a Bayesian network. So here in Netica, we used to say, if you're entertaining a test to the system and you have a press perturbation or an input to weeds that favors weeds, the qualitative models will predict an increase in fire intensity, tall grasses, short grasses and forbs, but with a little bit of ambiguity, and complete certitude in a demise of evergreen trees and shade. And that agreed perfectly with the known dynamics of the system. And particularly, here's a system with native tall grasses that when the understory fire goes through, it does not kill the overstory evergreen trees. But if the tall grasses are replaced with this invasive weed called gamba grass, which was imported from Africa for some harebrained reason, the fires from this grass reaches far up into the canopy and absolutely burns out and does a stand replacement fire for the terrestrial vegetation. So the tropical savanna then is held in check by the invasion of gamba grass and never resets back to a forest. It will forever be gamba grass until you remove gamba grass physically. And so that's the great fear of the mine site rehabilitation, is that an invasion of gamba grass basically means it's game over, because you'll never get a terrestrial forest, tropical savanna ecosystem there again. So that fear is held within the confines of this model as an input to tall grass here. So here is only a 5-variable model that held all of the relevant complexity that was elucidated in the first workshop. That complexity in their minds led them to argue for this high resolution of these variables. But the take-home message is that a simple model can actually do the job better than a more realistic, highly resolved model. So given that, we could do a risk assessment of the larger system. We took these core models and we found that the immature system of evergreens would evolve into a mature system where there was no longer influence from fire intensity in tall grass, when the tall grass was not an invasive weed, but just the native weeds. Then the evergreen trees would be immune to disturbance until they became old and died. And then they would become senescent, and then a normal fire would take them out. And here you can see a burned out trunk, because after about 40 years, the bark splits, and then the fire gets into the bark and the tree burns up and they fall over, and then a new stand will come in. That's the natural cycle of old tree, mature tree, old tree, falling fate to fire, back to a young forest. And that's the cycle. That's the natural cycle. But if gamba grass comes in here and replaces the tall grass component with this highly flammable and intense fire generating weed, then the system gets shunted off here and it's held in this steady state weed invasive system without a tropical savanna. So on top of this simple 5-variable model, we bolted in other aspects of the system, like the soil, organic levels, the grain size, the water stress of the system, all the things that the cyclones, all these other variables here, we bolted on to the ones in blue. So the black ones, we bolted onto it, to the core model, and we use that to then run our risk assessment and management intervention predictions. And so we looked at 3 different management options of weed control, fire control, and weed and fire control with an immature forest or a mature forest. We didn't need to worry about the senescent forest because that was outside the window of the risk assessment for the mine site. And we could then predict whether or not different management actions would have the desired effect on the system. And what we found was that weed control was much more effective than fire control for trees and tall grasses because of the ambiguities in the system. Weed and fire control combined were no better than weed control alone. So this showed that weed control was the most important management action to focus on, whereas fire control before the risk assessment was thought probably to be the more important thing. Now, based on the 5-variable core model, fire intensity will have different outcomes based on tree maturity and presence of gamba grass, which is what I just got through explaining to you. Then we shifted from the terrestrial system to the aquatic system. And here the key problem was magnesium or manganese getting into the surface groundwater out into the surface water. Now, they did lots of single species challenges to different doses of manganese and found the exposure levels that caused a dose response curve inflection that they could then lay a boundary on that was for management. And so they did that for many different species, and then they did a species sensitivity distribution, arraying most of the species that they've been measuring in the system. Now, based on that, they decided that manganese was probably something that was really important to focus on. Here they have all the direct effects for single species, but they wanted to understand a larger ecosystem context. So they set some levels of likely thresholds, and then they wanted to understand how that might be, how that information could then be inserted into an ecosystem context. Now, this was their conceptual model of how the larger ecosystem worked for the aquatic system. And I had the same hard job of corralling that level of complexity down to a functional relationships that could be more simply portrayed and have direct, could lead to something that was more plausible or measurable or understandable. And this was the model I finally came up with these different variables here. I won't go into much detail with them as I did with the terrestrial model, but it has all the usual suspects of an aquatic ecosystem, but maybe not so much for you guys, having crocodiles as the top predator up here. And that's probably the most highly valued variable after fish. So these are the high value variables, and they wanted to know how different concentrations of those chemicals would affect this system. So we did the same sort of thing with magnesium input into the system, and we had it just on phytoplankton, or we had it on these different functional groups that came out strong in the assays, and then we did it with phytoplankton and those other functional groups of planktonic invertebrates and still water invertebrates. And phytoplankton alone gave the clearest impact, especially to highly valued crocodiles and fishes. So that was an interesting result that they're going to be following up with monitoring programs. Now, the conclusions from this work have come down. I decided, I mean, we have a journal article, but I found it interesting because the scientists that I was working with had really no direct knowledge of this technique before. They were used to more reductionist or linear risk assessment approaches. And I was delighted to see that they really enjoyed the whole of ecosystem perspective. They really embraced the big picture and appreciated the value of how their knowledge of small components of the system fit into the bigger whole. But on top of that, the qualitative models were used to prioritize key management actions, controlling weeds, and highlight key indicators for monitoring. And we believe now collectively, this is not just me talking, that the best environmental outcomes are achieved through decisions with multiple perspectives and multiple lines of evidence. The results of the qualitative models are not to be used in isolation, but to support other risk assessment approaches, specifically good statistical approaches, and should guide data collection to test model predictions. So these models need to be falsified. You just can't take a qualitative model and trust it like any model, of course. Ecological risk assessments typically are linear. Qualitative modeling was valuable to explore feedbacks and cumulative effects, which can sometimes result in unexpected or undesired outcomes. And with that, I'll hand it back over to my hosts. And I guess there's maybe time for questions. And I'll stop sharing my screen, I guess, too. How do I do that?
Absolutely. Thanks for your wonderful presentation, Jeff. Have we got any questions from the audience?
Well, I certainly do. I love the presentation, Jeff. Thanks very much. The slides about the qualitative behavior and the multiple stable states and stuff. That's why I got into ecology, and that first draft of the ecosystem there with the spaghetti plot. That's why I left ecology. I think.
Oh, you should have met me before you left. Also, can you shift your camera? Because all I can see is the top half of your forehead.
That's really all anybody should have to see there. There, okay. That is very distracting. So what's a high value variable? What do you mean by that?
Oh, high cultural value. I mean, you ask the Aboriginal community, what do they want? They want to make sure that the crocodiles are there.
So it's kind of it's kind of remarkable given that Americans can't seem to resist building houses or rebuilding houses on floodplains, that the Aboriginal peoples knew that these sites were sickness inducing. Are there floristic effects that you can see from the radiation, the Ranger site?
I don't know. I only visited that mine site once, and resulted in a helicopter flight over it and a tour of the revegetation.
Plus that's after the mining, so you don't really know what it looked like floristically before.
No, I don't.
Why is it there? Is
I
it a
don't.
volcano or something? What's why is it there in the first place? Do we know?
Oh, just a geological concentration of uranium near the surface. I don't know exactly why. I never studied that aspect of it.
So
Despite myself having a keen interest in geology, I didn't look into that.
right.
But these are very old mountains. I mean, there used to be mountains that rivaled the Himalayas in Australia that are now near sea level. So there is, huge very old geological
Right.
formations. Here's some of the oldest on Earth.
Australia has the oldest rocks still on the planet, right? I mean, that's what we think. So that first draft, when you convert that to the simpler sign diagram, that's very exciting that you can do that. And you say, oh, it just takes extracting them from their taxonomic prejudices. Basically, it's function, not taxon.
Yeah.
The real question is that really reproducible? I mean, would you really genuinely think that if you did it in one place with one set of people, and you had an equivalently qualified set of people, maybe a smaller group somewhere else, are they really going to, look into your heart? Are they really going to come up with the same thing? Or would it make
probably not exactly, but hopefully functionally equivalent if they hold those principles to heart. And I think that's an impossible experiment because you would have to essentially make a control of myself. Well,
do you have a sister?
You would never get the same exact model. No, you would never.
Okay, well that's
Probably.
yeah. So
Probably, and that's one of my biggest problems is the hit by bus, or someday I'm going to retire, and there's not a lot of people out there who've taken qualitative modeling to heart.
Sure.
I'm one of the few. I could probably count on my two hands the number of people that are dedicated to it. And when you first get a neophyte at it, they go for the 30 variable model almost every time.
Right. Less is more, it turns out. So I noticed that the system that worked beautifully was the competition system, where it's just grasses and herbs and evergreen trees. Of course, trophic systems or predator-prey systems, they tend to be messier. So are the models that you're talking about and these qualitative mathematical models, are they underlying? Are they Lac-de-Volterra style models, or is there something else?
Sure. Yeah,
Just
Lac-de-Volterra.
Flavored Lac-de-Volterra.
Sure.
Okay. And
That's the backbone of it.
the backbone. Okay. So ratio dependence, you say no way, or
Yeah, ratio dependence is just the negative self-effect on a variable.
okay, that's quite interesting. Okay, that's I guess that's my main questions. I have some discussion. I'm sorry, I was so excited. I got excited there. I had to interject.
I like excitement. And you should tell the audience that hopefully if my travel gets approved, I'll be coming to your department the second week or the third week, depending on the count of April, and giving a seminar on this technique.
Right. Well, that'll be very exciting. I'm worried that I'm worried that we're going to be on strike, of course. Yeah, you have.
Yeah, so nice to meet you, Jeffrey. I loved your presentation, Ricardo here. And
Ricardo.
I saw that you performed some tests with aquatic organisms. And why? So this is
Not me, my co-author.
So why didn't you consider the soil organisms for ecotoxicological tests? I saw that your main your main aim is to promote the reforestation of the area. So you need to be soil biota. You need to have soil fauna to maintain this this vegetation. And there are a large number of organisms that we can use in terrestrial ecotoxicology to evaluate the harmful effects of uranium or other contaminants such as manganese. So I realized that your focus was on aquatic organisms, but I would like to ask you, why not soil organisms if your focus is revegetation?
Yep. So soil biota did come up in the workshop, and I had a variable for it, and there's lengthy discussions about it. But when I went down to create the core dynamics, I found I didn't need it. But you'll see that I added it back in to the core dynamic as an input variable. So maybe I should go back to sharing screen. So it's not as though I didn't leave it out. I just didn't enter the core dynamic. In the core dynamic for the tropical savanna, we needed to capture the fire dynamic, because gamba grass, if you have gamba grass, you don't have a forest. If you have more or less of a constituent of the soil biota, you'll get probably, you wouldn't imagine no forest versus some forest. It'll be maybe more healthier tissue growth or less healthy tissue growth. But we were looking at stand replacement fires, the big picture, right? And then these other things, which perhaps more subtle in terms of dynamics. So not to say they're not important, but I was looking at the dynamics that controlled the transition from mature to senescent to young and back again, and how that could be derailed by intense fires. So I'll just say that I did show, oh, what have I done here? I guess I am sharing the screen. So I got excited and hit the wrong thing. Oh, I guess I'll do it. Yeah, so soil biota. Here, SB, can you see that?
No, we don't think you're sharing.
Oh, I'm not sharing. Darn it. Well, what have I done? There, yeah, okay. Oh, there it is, share. Okay. Here we go. So there it is, soil biota. Soil biota here plays its role. SB, can you see that? And SB is affected by water stress and surface roughness. Now, beyond more detail in soil biota, we would have to unpack that. And I'm willing to do that with any of these sub-processes. My view is that you can take any one of these composite variables and unpack them and make a model just about them and find out what that level of complexity means to the larger scale. So soil biota has organisms that live on time scales that are much different than the mature, well, this is like a 40 to 80 year cycle here, whereas soil biota has variances that are at probably a quicker time scale perhaps, but maybe not so if it's about the buildup of organic matter, which would be hundreds of years or thousands. So you just have to set the time scale for the model and then understand that some variables are not going to play a big role at the time scale that you're entertaining. The time scale of the model in front of us was at the 40 to 80 year time scale. Okay. And so fast processes need to be unpacked at a shorter time scale, where these longer time scales then become constants with respect to the shorter time scale. So when you do this qualitative modeling, you're always shifting between what you call the relevant subsystem. And when I do my teaching courses, I spend a lot of time talking about the significance of a relevant subsystem. This is the relevant subsystem of the tropical savanna. And then you can bolt onto it faster and slower subsystems depending upon your interest and your research or management questions.
Did you buy that? So, I mean, that's kind of remarkable, right? So I recognize the value of that. Soil biota, I mean, to a soil ecologist, you know, it's kind of like saying, you know, everything and nothing at the same time, right? It's how they tolerate that?
Huh? Do what?
The soil biota is, that's all sorts of things, right? It's the chemistry in the
Of
soil,
course, yeah.
and it's, you know,
How silly to put soil biota into one variable. I mean, it's almost means nothing, right?
well, but
But
that's
for here,
so
it meant about with respect to delivering surface nutrients, because surface nutrients were what was going to feed short grasses and forbs and tall grasses. So we've already ignored all the other aspects that soil biota are important for beyond grasses, forbs, and tall grasses.
Erosion processes.
So it's really an ecosystem services style model, really, because you're not talking.
Yeah, if you want to call, well, that's one way to put it, but this was identified as the important dynamic by all the people in the room.
Right. Was
these photographs. This was the mythology in their head that they wanted to capture, and they thought they had to get really complicated to catch it.
You know,
but I said, oh, I can do that in four or five variables, and then bolt onto on top of that, the required complexity for the risk assessment and the management interventions.
So, I mean, if you have evergreen trees as one of these components, but somehow there's a disease that comes in and it only kills the hemlocks, that sort of thing is sort of beyond scope, I guess, or would need to be modeled in its own right, I suppose.
We had the same problem with the aquatic model, where not all phytoplankton suffered from magnesium.
Right.
And they wanted to blame, the scientists wanted to blame that on the fault of the qualitative modeling. I said, no, that's a fault of aggregation. That's just resolution. If you want to make a model about the 50 species of phytoplankton of interest, then let's do that.
Right. So it's like all modeling exercises. It's an argument.
You can't. The beauty of a mathematical model is it's an abstraction of the world that is simple enough to use.
Yeah.
To say that a simple abstraction means you have to concede many layers of reality to get to something that's useful.
So, well, I guess we're 15 minutes over time. Well,
but I finished my talk on time, so that's one mark on my pint
Sorry.
count.
Sorry, it was me that was dragging us into the overtime. Thanks very much, Jeff. I know it's late there. You may need to peel off, but I guess we can have Ricardo's talk now. Would that be reasonable? Let's see.
All right. Bye, everybody.
Are you actually going to leave? I thought.
No. I mean, just for now. I mean, thank you very much. I'll listen to Ricardo, but I'm not going to attend your lunch. So.
Right. That would be hard indeed. Okay, so let me steal back the focus. So the introduction for Professor Ricardo Cesar is, well, he's a geographer and a geochemist, more chemist than biologist, I think, and a professor at the UFRJ, which is the Federal University of Rio de Janeiro, and the Geosciences Institute. He's been highly multidisciplinary. He's been working in ecology and toxicology and engineering. He speaks, 18 languages. Let's say just German, English, and what else? Portuguese, of course. He was telling me about some of these experiences yesterday at lunch. He's been working on soils and rivers and estuaries, and specifically the effects of mine tailing deposition there. Not just in Brazil, I guess, also other places as well, or just Brazil, yeah. So around, but especially now, we're really interested in the Brumadinho and other mine dam failures in Brazil. So I guess your talk title, not to delay it any longer, Ecotoxicological risk assessment of metal and hydrocarbon pollution in eutrophic sediments from urban tropical lagoons. And let me get your slides up. Oh, that's not your slides. Oh, it's not open. This- Get out of your way. Put your
May I sit down here?
sure. Adjust the camera to or to the top of your head as you choose.
So I think it's better. So everyone, can you see me? Yes.
Yeah.
So good morning, everybody. I'm Ricardo Caesar, and as Scott said, I am a professor of the Federal University of the Rio de Janeiro. And today, I'm going to present to you the work Ecotoxicological assessment of metal and hydrocarbon pollution in eutrophic sediment from urban tropical lagoons. So regarding metal pollution, metal can have two types of sources. The geogenical sources are commonly related to volcanic eruptions and areas that were submitted to intense metamorphism in the geological past. And because of that, they can contain deposits of metallic sulfides, such as cinnabar, which is mercury sulfide. And the weathering of these rocks containing these deposits can release ionic forms of metals to the environment, causing ecological damages. The anthropogenic sources of metal pollution can be related to domestic sewage, especially along the Brazilian coast, but not only domestic sewage, but also industrial waste, port areas, garbage deposition, mining tailings, coal combustion, and dentistry. In terms of hydrocarbon pollution, here in this presentation, I'm going to emphasize the PAT compounds, the polycyclic aromatic compounds. Such compounds have high toxicity. They are neurotoxic and carcinogenic to human beings and biota, and then can have two types of sources. The pyrolytic sources, which are related to atmospheric deposition. Such compounds can be emitted as gases or in the soot composition by the vehicle's exhaust, or they can be derived from the burning of materials such as garbage. And the petrogenic sources are associated with field discharge or navigations activities, gas station, and urban runoff. Over the last decades, the expansion of urban areas along the South American coast has increased the inputs of domestic sewage, industrial waste, and garbage to fluvial and estuarine systems, causing silting processes, contamination, and eutrophication of these ecosystems, and also compromising important ecosystem services. In the Rio de Janeiro city, some engineering interventions were promised to fulfill the demands of the Olympic Games, but many of these interventions were not performed. Nowadays, the situation is especially critical in some lagoon systems of the Rio de Janeiro city, such as the lagoons of the Jacarepaguá complex and the Rodrigo de Freitas Lagoon, which is very famous lagoon in our city. Most of geoenvironmental studies focus on soil contamination or sediment contamination are widely based on total chemical analysis, metal speciation, and metal sequential extractions. Even though such approaches are very important, they are not able to evaluate the synergistic effects of contaminants and ecological damages. In this context, in this respect, the ecotoxicological test can complement the results derived from chemical analysis. And sea urchin, amphipods, algae, and bacteria are widely used as test organisms in the marine ecotoxicology. The use of such organisms are due to their ecological relevance, short life cycle, and simple cultivation at the laboratory. So today I'm going to present you the results relate to the evaluation of potential toxicity levels of metal and hydrocarbon pollution and bottom sediments from 2 tropical lagoons in the Rio de Janeiro city, Rodrigo de Freitas Lagoon and Tijuca Lagoon. So the first one is the first lagoon is the Rodrigo de Freitas Lagoon. I'm going to show you here some results that are already published in the Environmental Pollution Journal. Here we have our Rodrigo de Freitas Lagoon. We have 60 sampling points of surface sediments in the Rodrigo de Freitas Lagoon. We performed the sampling of sediments 1 year before and 1 year after the Olympics in order to evaluate the benefits of the engineering interventions that were performed in this lagoon. The sampling of the sediments was performed by using a Van Veen dredger, as you can see here. And here we have the aspects of the sediment samples that we collected in this lagoon. Here we have the spatial distribution of sediment sampling points along our lagoon. And also we can see here that we have 3 watersheds that drains to this lagoon. The blue one drains the Rocinha favela, which is the largest favela in Brazil. And here we can see also the beach, the Leblon beach, the Ipanema beach, and the Copacabana beach. Here on the other side, here the Leblon beach, Ipanema beach, and here Copacabana beach. And Rodrigo de Freitas Lagoon has a connection with the ocean through the Jardim de Alá channel. That is the only connection between the lagoon with the ocean. So in order to support the 60-meter depth. Yeah, yes. In order to support the interpretation of the ecotoxicological data, we determined the texture of the sediments. We also determined total matter concentrations. These concentrations were compared with the threshold with the threshold limits defined by Brazilian law for dredged sediment quality. And we also determined total organic carbon and nitrogen concentrations. Here I'm going to show you the results of 2 types of ecotoxicological tests with marine organisms. This first one is the acute test with the bentonic microcrustacean Tiburonella viscana. We got these organisms at a reference area in the São Paulo coast. The organisms were submitted to acclimatization for 3 days at the laboratory. The test duration is 10 days. The test system consists of 100 milliliter of sediment and 400 milliliter of seawater. The test was run with 3 replicates and 10 adult organisms per replicate. The test was also run under controlled temperature, constant lighting, and aeration. And by the end of the test, the mortality of the organisms is evaluated. So guys, just a second. I forgot my bottle. The second test is the chronic test with embryos of sea urchin. This is a chronic test using recently fertilized sea urchin embryos. We got these organisms at a reference area, also in the São Paulo coast. The organisms were also they were also submitted to acclimatization at the laboratory. our systems, these test tubes, were composed of 2 ml of sediment, a plankton sieve to prevent the direct contact of the larva with the sediments, and 8 ml of dilution water, seawater. The test was run with 4 replicates per sample, and after 18 hours of the test, we should verify abnormality in the larval development. Well, in order to obtain the male and female gametes, we have 2 options. We can have an injection of 2 ml of potassium chloride or electrical stimuli. We chose electrical stimuli to obtain such gametes. The female gametes and male gamete are mixed in order to have an egg, or not have the eggs. And such eggs, such fertilized eggs are exposed to our test tubes, our test systems. And by the end of the test, we should verify the morphology of the larva, and this is the expected morphology in order for us to evaluate any abnormalities in the larva. So here we have some results related to total organic carbon in the sediments of Rodrigo de Freitas Lagoon. We see that northern sediments are more organically enriched compared to the sediments collected in the southern sector of the lagoon. This phenomena is due to the presence of the Jardim do Alá channel in the southern part of the lagoon. So in the southern part of the lagoon, we have more marine contribution, more aeration that promote the oxidation of the organic matter, and because of that, the contents of organic carbon are lower in the southern sector of the lagoon compared to the northern section. Those organic matter contents are greatly correlated with mud content. So the northern part of the lagoon, in the northern part of the lagoon, the sediments are extremely mud and organically enriched, while the sediments from the southern part of the lagoon, they are sandy. They are more, they suffer more influences from marine contributions, and the organic matter contents are lower. Some interventions, some engineering interventions were performed in this lagoon because of the Olympics. These interventions were planned to reduce sewage, domestic sewage inputs to the lagoon. But when we see here the organic carbon contents 1 year before and 1 year after the Olympics, we see a relative increase of total organic carbon content, despite the intervention that were performed in this lagoon to reduce organic matter inputs, domestic sewage inputs to this lagoon. Our main hypothesis is that most of this organic carbon that is present in this lagoon comes from primary production. We determined carbon and nitrogen isotopes to determine the origin of the organic matter. And after the Olympics, most of organic matter come from primary production. So the bottom sediments of this lagoon need to be urgently dredged in order to minimize eutrophication and minimize the primary production. Actually, they performed the dredging of sediments in the northern part of the lagoon, but this intervention was not enough. And the practice of aquatic sports during the Olympics in this lagoon was performed in the northern part of the lagoon, where the situation is more critical. Here we have the results related to zinc and copper concentrations in the Rodrigo de Freitas Lagoon. Again, the northern part of the lagoon had higher zinc and copper concentrations compared to the southern part of the lagoon. So we have here a great correlation between mud contents, organic matter contents, and metal contamination. Organic matter is able to form stable complexes with metals, and because of that, the northern part of the lagoon is more metal contaminated. This yellow line means the limit of the Brazilian legislation for dredged sediment quality, and most of the samples are above such limits for both copper and zinc. Copper and zinc are good indicators of domestic sewage inputs, since they are micronutrients, and when we compare such concentrations with the threshold limits of the Brazilian law, we can see that such concentrations are really high. Here we have the lead and nickel concentrations. Most of lead concentrations are also above the limit of established by Brazilian legislation. Lead is a very toxic metal, more toxic than zinc, more toxic than copper, and such results are in fact an issue of concern. And here we have cadmium and chromium concentrations. Before the Olympics, cadmium concentrations were lower than detection limits, but after the Olympics, the cadmium concentrations significantly increased. When our hypothesis for this phenomenon is that the dredging intervention that was performed in the northern part of the lagoon, this intervention resuspended some more contaminated sediment layers, subsuperficial sediment layers that were more contaminated, were resuspended in the water column, then thus forming another surface sediment layer, which is more contaminated than before. So the way this intervention was performed was not adequate, was not appropriated. And regarding chromium concentrations, most of the concentrations were in agreement, were below the limits established by Brazilian legislation. So we can consider that chromium concentrations are less relevant compared to other metals. Here we have the spatial distribution of the mortality levels of amphipodos, our Tiburonella viscana. And we see here that the spatial distribution of this toxicity is greatly correlated with metal distribution. We can see here the distribution of mercury concentrations in bottom sediments, which are almost coincident with the spatial distribution of mortality of amphipodos. On the other hand, when we see the toxicity to the embryos of sea urchin, we see a very high toxicity levels and some generalized toxicity for both northern and southern sediments. Our hypothesis is that this toxicity to the sea urchins are related to ammonia released from the sediment, which is typical from eutrophicated areas.
Those anomalies from the developmental.
Yes.
And those are the big percentages.
Yes. So here we're gonna see our second lagoon. Rodrigo de Freitas Lagoons is a more famous lagoon. If you visit Rio de Janeiro, you are probably visit the Rodrigo de Freitas Lagoon. But here we are going to see a less famous lagoon, which is the Tijuca Lagoon. Most of these results are submitted to publication in the Environmental Science and Pollution Research journal. And here we have our Tijuca Lagoon. Tijuca Lagoon is part of the Jacarepaguá Lagoon complex in the western Rio de Janeiro city. So here we have our lagoon, and there are also here other lagoons, the Jacarepaguá Lagoon, which is very, very, very close to the Olympic complex, the Camurim Lagoon, the Marapendi Lagoon, and Das Taxas Lagoon. There is a deep social contrast in the surroundings of the Tijuca Lagoon. So here we have the Pedras Favelas, the Musema Favela on one side of the lagoon. And on the other side of the lagoon, we have shopping malls, business buildings, golf clubs, and townhouses and apartment complexes. So there is a deep social contrast. On one side of the lagoon, we have favelas, very poor people, and on the other side of the lagoon, we have very rich people living in a very sophisticated apartment complexes.
And they have views of each other.
Hmm?
These two groups have views of each other.
Have what?
Views. They can see
Yes,
each other from across the
yes, yes. But they don't care. Unfortunately, they don't care. Here we have our sediment sampling points along the Tijuca Lagoon. We have 23 sampling points of surface sediments. The sampling was performed in the winter season, which is the worst scenario, the worst case of ecological risks. We use the same Van Veen dredge used for collecting sediments in the Rodrigo de Freitas Lagoon. And here I'm going to present you the results related to the ACU test with Amphipodos, Tiburonella viscana, the pH determination, and also physical and chemical characterization of these sediments. So here we have the results related to texture determination, similar to the Rodrigo de Freitas Lagoon. We have here two different compartments in terms of sediment texture. We have a sand compartment, which is more influenced by marine contributions and the rivers of high energy. And on the other hand, we have a mud compartment that receive less contributions of marine waters, and the rivers that drain to this part of the lagoon are rivers of low energy. And because of that, we have two different compartments, a mud compartment and a sand compartment. The distribution of the texture of the sediments influence the organic matter distribution inside this lagoon. So the sand compartment is more sandy, while the mud compartment is more organically enriched. When we see the spatial distribution of pH values of these sediments, we can also see that the mud compartment is more acid, while the sand compartment is not so acid. This is a consequence of the eutrophication processes. So in the mud compartment, we have more organic matter contents due to eutrophication, due to sewage, due to domestic sewage inputs, and because of that, the pH values are extremely low in this mud compartment. So here we have the spatial distribution of zinc and copper concentration in the Tijuca Lagoon. For both metals, the concentrations found in the mud compartment is 3 times higher compared to the sandy one. Again, we have here a great correlation between mud contents, organic matter, and metal contamination. About 70% of the sample are above the limits defined by Brazilian law for dredged sediment disposal. And we also applied here some geochemical indexes for evaluating metal contamination levels. But unfortunately, I don't have time here to explain, for better explain this index. But the application of this index, geoaccumulation index, metal enrichment factors, they showed that we have great geochemical anomalies of zinc and copper in this lagoon. Here we have the spatial distribution of mercury and lead in the Tijuca Lagoon. Mercury concentrations in the mud sector of the lagoon were 4 times higher compared to the sand compartment. So again, we have a great correlation between mud contents, organic matter, and metal contamination. Only 2 samples were above the limit established by Brazilian legislation for sediment quality, those ones here. And regarding lead concentrations, the concentrations found in the mud sector is 3 times higher than that found in the sand compartment, and only two samples, those ones here, were above the limit established by Brazilian law. And the application of geoaccumulation indexes, metal enrichment factor, also showed that such metals have important geochemical anomalies. And the presence of these metals in this lagoon is related to industrial waste that come from the rivers that drain to this lagoon. Here we have the spatial distribution of chromium, arsenic, and nickel. Here we have the same pattern of metal distribution. So higher concentrations in the mud sector of the lagoon compared to the sand one. Most of the concentrations of these metals were in agreement with the limits established by Brazilian legislation. So even though we have some hot spots of contamination, those concentrations seem to be less relevant. And another important aspect to see here is that the morphology of the lagoon also play an important role in metal distribution and organic matter distribution. So this area here, for example, the P5 sampling point, we have here in geomorphology, we call that a back. So it is an area whose hydrodynamics is lower because of the morphology of the lagoon. So in areas like this, the concentrations of metals, the concentrations of organic matter tend to be higher. Actually, the sampling point here in the sand compartment is an exception inside the sand compartment because of the morphology of the lagoon, who tend to induce here a lower hydrodynamics. Here we have the spatial distribution of PAT compounds concentrations. Again, by following the same tendency, the mud compartment had higher concentrations compared to the sand one. Here we have a hotspot of contamination in the mud compartment. This is the P10 sampling point. Most of the P8 compounds that we found here are light P8 compounds, phenanthrene, fluorantane, and anthracene. So these PAT compounds are, we consider light compounds. Unfortunately, I don't have time to explain this here, but it is possible to determine the origin of the PAT compounds by calculating ratios between phenanthrene, anthracene, fluorantane, and pyrene. And most of these compounds that are present in this lagoon are of pyrolytic genesis, so atmospheric deposition, which is typical of very urbanized areas. But also we also have some contributions of navigation activities in this area here of the lagoon. So here we have the spatial distribution of the toxicity to amphipodos. The toxicity to amphipodos were not correlated with metals. The toxicity was not correlated with PAT compounds. Here we have a generalized toxicity, a very high toxicity, and a generalized toxicity along the entire lagoon. We have a mean mortality of 50%, which is pretty high. Only 3 samples were not considered toxic to these organisms. Even though this toxicity is not greatly correlated with metals and PAT contents, we found a great correlation with organic carbon contents and nitrogen contents, which led us to suppose that the toxicity found in the tests are related to domestic sewage contributions. But there are some substances that are commonly found in domestic sewage that were not quantified in these studies, such as hormone and pharmaceuticals. So we cannot ignore the role of metals and PAT compounds in the toxicity. We have some concentrations that are above the limits established by Brazilian legislation. Our geochemical indices also indicated that we have great geochemical anomalies, but for sure, metal and PAT compounds have some influence in the toxicity found in the tests, but sewage contributions in this case seem to be more important, especially those substances that were not studied here, such as hormone and pharmaceuticals. So on my final considerations, texture, organic matter contents, and probably sulfides, which are typical of eutrophic areas, probably played a crucial role in the bioavailability and geochemical behavior of metals and PAT compounds. Compounds not determined in this work and commonly found in domestic sewage might play a vital role in the toxicity. Toxic gases such as methane, ammonia, and hydrogen sulfide probably influence the toxicity as well. And where are the benefits of the Olympics? But in the case of the Rodrigo de Freitas Lagoon, after the Olympics, the situation is not better. She's worse compared to the situation before the Olympics. And further investigation is mapping metal and PAT pollution in other South America tropical lagoons in order to support decision makers in actions of environmental control and define areas to be first chosen for restoration actions. So those are my contacts, and I would like to thank you for your attention.
Thank you very much.
Was I on time?
You did an amazing job on time. So I have a couple of questions. So you said the PAHs were from atmospheric deposition of people burning stuff.
Yes.
Like
People burn garbage in the favelas. Yes, garbage.
sure. And the heavy metals that are in there, they're coming from industry.
Yes,
So
there are.
upriver somewhere.
Yes, actually, the Jacarepaguá Lagoon systems is located at a coastal plain, which was formed during the Quaternary period,
Right.
during the sea level oscillations
Right.
during the Quaternary period. So it is a coastal plain.
Sure.
And in this coastal plain, there are many industries, and
They're still
yes,
emitting
to the
stuff?
rivers.
So the lagoon would eventually clear itself out, presumably, but it's still continuing.
Yes,
It's not just this one.
and domestic sewage is also a problem.
Well, yeah. But the heavy metals aren't coming from domestic.
Yes,
They
zinc
are.
and copper, because they are
Zinc.
micronutrients, and because of that, they are abundant in sewage.
Sure. So you said there was higher, lots of sites that were higher than limits defined by Brazilian law. So my question is, those limits, what were they designed to protect? I mean, are they
human exposures?
No,
for
no, no,
swimming,
no.
Or ecological? Or
They
dredging, or-
are related to the limit of low probability of adverse effects on aquatic biota. So
Oh, aquatic.
yes,
So
yeah,
not
they
just-
are focused on aquatic biota.
Are people upset about this or not?
Sometimes I cannot understand Brazilian people because
Yeah,
we
well,
should
to
we should care, but some people care, other people do not care, and the reality is that so much money was spent for the Olympics in order to make the restoration of these lagoons, but we see that the benefits of the Olympics didn't come. That's the reality. At least for the
economic benefits.
Hmm?
The economic benefits or the?
the environmental and ecological benefits.
Okay.
Yeah.
Well, I mean, dredging is very iffy. Sometimes it makes things better, sometimes it makes it worse. So,
It depends on the way that you perform the dredging. For example, you can use a suction,
okay,
so you for you not to
Right.
resuspend sediments,
right,
but it's more expensive.
right.
So we have to before doing an action like this, we have to understand the space and distribution, the better places to perform the dredging. In general, we don't have so much money, so we have to choose the proper techniques and the proper locations to perform such kind of engineering intervention.
So.
No problem, Scott.
So it looks like. So actually, okay. So you talked a lot about the chemical species, but didn't actually say much, or maybe I missed it about what actually lives there. So there are fish, I guess.
Yeah, we still have fish, some gastropods also, but in the Rodrigo de Freitas Lagoon, the situations is a little bit better. So we have mangrove areas, and also have mangrove areas in the Tijuca Lagoon. So
are
we
these-
have some species that are is still there, but many of them were already lost.
lost.
Yeah,
Okay, so they're not
especially
thriving.
fish species.
You wouldn't call them thriving populations. I mean, in New York Harbor, for instance, the pollution is horrible. I mean, but the species that are there
Mhm.
are actually adapted to these heavy metal concentrations. If you take them out of the head of New York Harbor and put them in clean sediment, they don't do as well because they're kind of adapted to the heavy
And
metal.
there are some authors that say that there are some genetic
Yes.
adaptations.
Yeah. There seems to be.
Yeah,
So
but
is that not true here? Because the species have been lost. So they're not thriving populations, they're just.
because
pollution
of course there are some species that are more resilient than others.
Right.
And they can have some adaptations. For example, there is a fish species. I know the name in Portuguese, but not in English. This acará, which is very resistant to pollution. So most of the fish individuals that we have there is acará because they are very resistant to domestic sewage. We also have alligators in the Tijuca Lagoon. They are very resistant to
So do
the
people
pollution.
fish?
They eat fish.
Do the people fish?
No.
They don't fish the Because
In
there's-
the Brazilian Amazon, yes, but here no.
But not here, because, but it is, I mean, probably it's not the heavy metals per se that's keeping the vital populations away, right? It's the organic. From the sewage, right? Would you say
I
that,
think
or
both.
both? You think it's both? So you think
both.
the heavy metals are actually. doing it?
Yeah, both. But
Okay.
in the Rodrigo de Freitas Lagoon, we determined the mercury concentration in fish mussels
Right,
of 2 different species,
right.
and we performed the human health risk assessment associated with the ingestion of mercury contaminated fish.
But do you think the
And the
mercury is-
results were not so good.
No, of course, but that just means humans should eat them, but the fish themselves, they can. accumulate
In
quite a
terms
bit.
of ecological risk,
Right, for the
to
fish
fish.
species itself.
okay. So in the Guanabara Bay, so some years ago, we collect some fish there, and we collect the blood of this fish, and we analyzed some anomalies in terms of the red part of the blood, hemácias cells.
Yeah.
I don't know how to say that in English.
Hematocytes.
Yes. And when we would evaluate some anomalies in the morphology of such cells, and yes, they will suffer the effects
Right.
of the contamination. We also determined mercury in kidneys, blood, brain, in order to determine the toxic dynamics
Right.
of, and yes, they really suffer
Right.
huge several effects. Yes. And we also performed say that in English. When we have the blood exam in order to verify immunological effects, for immunological. Yes. So we have a partnership with the veterinary department
Right.
science, and then they help us to
So do you
verify
think
that.
the dredging should have been done for the Olympics, or
They should have been done, but with suction.
better? They should have been better.
Yes, but it is more expensive. But
Very interesting.
so
Yes, Ricardo. Very interesting talk. Thank you.
thank you.
Can you
Jeff.
hear me?
Yes.
I was interested in how you chose the locations for your sample points through the different estuaries. What was the spatial considerations
Mhm.
that were taken to locate sample spot points?
Just a second.
Didn't look random, did it?
The selection of the sampling points was considered when we have fluvial contributions, such as rivers, that the mouth of the rivers, the contact of the lagoons with other lagoons. In the case of Tijuca Lagoon is part of a lagoon complex, so it is connected to the ocean, to other lagoons. So we try to verify fluvial contributions, marine contributions, and also the morphology of the lagoons were also considered when we have selected the sampling points for sediments.
Did you have distinct spatial strata mapped out beforehand? Or were you doing it based on a topographic or looking at the plan view of a map to point to these locations?
Yes. We firstly we saw the lagoon in a general map, not a special map, not a special map, and then we see the morphology of the lagoon, the mouth of the rivers, the position of the ocean in relation to the lagoon, and after that we chose the sampling points. But actually we don't have so much money to perform a more complex sampling. But in environmental biogeochemistry, we have a technique to mapping metals in soils and metals in sediments by using a lower number of sampling. Most of the geologists in the 19th used this technique for searching for minerals in Brazil. So people from medical geology medical geology and environmental geochemistry has used this type of technique to mapping metal concentrations and pH concentrations in impacted environments.
I was interested in this question because it's something that we're doing a lot of work on here in Australia, and for marine environments is to it's called spatially balanced sampling designs. And these, if you can attain a good spatially balanced sample, it reduces spatial autocorrelation. and it makes for the highest possible efficiency of your sampling effort with respect to the strata that you want to gain information from. And it looked like a great example there because it looked like you had a great example where it could have been employed because it looked like you had very clearly defined gradients of grain size with respect to mud, or location strata with respect to mouths or beaches of interest. And without much effort, you could have taken, well, whatever sampling effort you have, it maximizes its information and efficiency. And it looks like an ideal application in your situation to use the spatially balanced design. And if you're interested in that, we've developed quite a bit of literature here that it actually was idiosyncratically developed in Oregon. And then when I came to Australia, I no, I didn't do it, but the people I knew were expert in it, and I had them correspond with the Australians. And so now we're using it all across our sampling in Australia for marine ecosystems. But it was primarily developed in terrestrial environments, water quality environments as well, out of the EPA in Oregon. If you're interested in that, I can put you in touch with the literature.
So Jeffrey, is it primarily a stratification strategy?
Yeah, but it is no. Well, it uses stratification as the grist for the mill, but it seeks to have samples that are maximally distanced from each other. And when you do that in a random way, then it allows you to do things like post hoc stratification. So what if you did your sample and you didn't realize, oh, the left half is different than the right half, or even something more insidious, that you have something more random polygon interspersed strata that you like to excise out, like land use that you didn't realize, or something else. You can do that post hoc stratification and still make rigorous, unbiased inference from your data points. But only if they're spatially balanced.
So Ricardo, can I ask, maybe this is a dumb question because I don't really understand what happened to the coast, but the size.
Can you get closer to your microphone?
Oh, sorry. So this may be a dumb question because I don't really understand, hydrodynamics or hydrology or water near the coast, but so the size of the watershed is usually, you only get the pollution that lands in that watershed, right?
Mhm.
It also settles down into the lagoon. So how big is the watershed that feeds this lagoon? Is it just this? I mean, you had lots of lagoons, so presumably only parts of the city go to each one.
You mean the contributions of the watersheds,
Yeah.
or the contributions of marine waters?
Well, the marine waters come back in from the canal, right?
Yes.
I was thinking of the watershed.
It depends on the lagoon, and depends on the characteristics of the geomorphology.
Right. And so they're all different.
Yes.
But they're mostly in the city, or they go beyond
in the city.
They're always in the city.
And
Oh.
All the time. Right. So is the ocean water is not considered polluted, is it? It's relatively clean.
No, not in these cases. Not in these cases. But
polluted.
at the Guanabara Bay, where when you got there, we were in the international airport, so you saw the
okay.
Guanabara Bay. So the waters of Guanabara Bay, yes, they are
Those are
highly
the marine
polluted.
waters are highly.
Yes.
Yeah, okay.
Yes.
Do they open up the inlets to the lagoons artificially to create flushing?
Sorry.
Do they take efforts to open up the lagoons to the ocean, like maintain canalways that might otherwise fill with sediment? Do they promote flushing from the ocean?
Yes. So this connection between the lagoons and oceans has generated so many problems for people who want to use the beach. So we have the proliferation of cyanobacteria, and these like hepatotoxic cyanobacteria, and also aquatic plants due to eutrophication. And during the summer, especially during the summer, such cyanobacteria and aquatic plants, they can reach the ocean, and also they can reach the beach, and then this is
So you want to keep them closed.
yes, yeah,
Oh,
complicated.
It's the
So
other
pay
way around,
attention
yeah.
if you go to Rio de Janeiro during the summer. Depends on the
so
beach where you
the
are.
near coastal waters are nutrient rich.
What's the word? What? Sorry.
The near coastal waters, the ocean waters near on the beach are nutrient rich.
Yeah, they can be contaminated with cyanobacteria
Hmm.
and domestic sewage, especially
Ah,
especially.
Yeah, so it's the things that are happening in the lagoon that they don't want to release into the ocean. Because that ocean is right by, Ipanema Beach, right?
Yes,
That's where
one
that
of the
girl-
famous
Right,
beaches
that where
in
that
the
girl
Rio de
is
Janeiro.
walking. So you want to keep that nice.
Yes. But I don't like Copacabana and Ipanema Beach. I don't.
You don't like those
No. I prefer other preserved, more preserved beach.
Yeah, questions, Jeffrey?
no,
If not, I guess we could adjourn for lunch. We're gonna go over to the pen factory. Will you, maybe you're, it's late there, isn't it? In Australia?
yeah, it's almost 11 o'clock at night.
Oh, yeah, well, good night then. You're not gonna see anything after this, I'm sure. Have a good evening.
Okay, thank you very much. It was a pleasure having this interaction. Very nice to meet you, Ricardo, and you too, Francis, and
Thank you very much, Jeffrey.
also our friend from Bogota. It was nice to chat with you earlier. And
Thank you.
also, Scott, I'll let you know when my travel is 100% confirmed, but I'm crossing my fingers it'll happen. So hopefully see you soon.
Bye-bye, Jeffrey. Bye-bye.
So
Bye. Have a lovely evening.
Bye-bye.
I guess I'll log off.
I would suggest keeping it on, Scott. Would you mind changing the slide, just one after this or the 2 slides afterwards, so we can at least leave the PowerPoint on for anyone that attends the Zoom call?
That should we just have blank space then?
Yeah. So if you
I
click
don't-
2 slides,
Yeah, I can do that, but I really don't want to because this
you
is
don't want to leave the computer logged on or something.
yeah, not in my name anyway, right? If I could somehow
Leave that on.
I could leave it on, but not in my name. Can I do
Now.
Oh, it didn't do the yelling at me. So we're recording now.
Yeah, it's recording.
So, and now for a man who needs no introduction, no. Or rather, so we want to talk about ecotoxicology today, or specifically about the problem that we have of explaining ourselves to others, which is to say, how to answer when someone says, so what about ecotoxicology? This is a big problem if you live in the United States, where there are plenty of people who are, maybe not quite as concerned as others for the welfare of Mother Earth. People who are interested in the economic impacts of some activity and have a trade-off calculation that's maybe different from the more commonly more commonly encountered among us academics and others. So
Sorry, Scott. I've noticed that your camera is not on, by the way, if you would like to turn that on.
Really, I kind of don't need it. If you want to see me smiling or frowning, I'll just.
I just think it's more engaging to be able to see the speaker, but it's up to you, obviously.
All right, I can do it. I just need to figure out how. Oh, now I need to escape to find the camera. Okay, here. Okay, there's the. See, the problem is if you turn on the camera, then you can see me. That's the.
Yeah, great. That's what we want.
Okay. If I'm far away, it's much better. Okay. So hide the video panel for sure, and hide the. Okay. All right. So when we're talking about ecotoxicology or ecotoxicology, we're really talking about chemical contaminations, chemical pollution, either usually of the aquatic environment, where it comes from agricultural runoff, which is probably the main source of chemical contamination, manufacturing byproducts, industries, or spills and leachates from mine tailings or fracking. Those are probably in order the most serious environmental contaminants in the aquatic environment. And in the terrestrial environment, it's similar, where spills and leachates from mine tailings and fracking are probably the highest problem. There's incidental toxicity, power line poles, and local contamination in so-called brownfields. And then there's hydrocarbon combustion, which does a lot for the aerial environment, or rather a lot to the aerial environment. These are roughly in order of how damaging they probably are. Forward. The chemical contamination is, of course, one piece of the environmental puzzle, right? The most serious thing that we do to the environment, most adverse and most consequential thing we do is destroy habitat or dissect the habitat. And then we also have harvesting and hunting. Chemical contamination is down the list, and lower than chemicals are thermal pollution from power plants, that sort of thing. And then maybe incidental mortality from isolated events, and then radiological contamination should really be the last, I suspect. When we're talking about ecotoxicology, there are really two schools, it's really almost two disciplines, right? There's the toxicant kinetics, the people who model what's going into the environment in terms of contamination and where those contaminants are going and flowing through the environmental cycle, or chemical cycles. And there's also population dynamicists who are worried about how many how reproduction might be impacted, or survivorship, and those two sort of schools of thought are really kind of talking past each other. Their models don't even aren't really even comparable. Toxicant kinetics is assuming that the population processes are slow, and you don't have to worry about changes, population dynamic changes to the populations. On the other hand, the dynamicists, the population dynamicists, are assuming that the toxicant is already equilibrated. It's where it is, and it's going to stay that way, and it neglects changes in the toxicant concentration. So we really need, of course, to integrate these two disciplines into one and create what is called ecological risk analysis, right? And the idea of that is it measures the effects on biological systems of these contamination events or processes. And the idea is to predict future consequences of those impacts. And of course, it's used across engineering to create minimal impact designs, to design mitigation strategies or cleanup remediation strategies. You have to certify that your population, that your site is clean enough for its intended use or not. Starting to worry that these slides are a different set than the ones I wanted. The emerging themes, and this is really the conclusion slide that I'll come back to at the very end, but the emerging themes from ecological risk analysis are threefold. The first is that we probably want to be focusing on not individuals as receptors, chemical receptors of these pollutants, but rather populations, and not either the whole ecosystem, because that's simply too hard. We really can only navigate a focus on populations. The second point is that we want to have a risk language that's using probability to express because it's not a guaranteed impact, right? It's a probabilistic impact that depends on, it could depend on things like the weather and the happenstances of exposures, and what the population is doing otherwise, irrespective of the contaminant. So that really requires this risk language, which makes it sort of an engineering problem. And finally, the third emerging theme in ecological risk analysis is that you want to look at, as Jeffrey said before, cumulative and attributable effects. So you don't want to have a situation where you've got a death by 1,000 cuts, where you have a lot of little impacts, but none of which is really very serious, but collectively they decimate a population. That you don't want to allow. You want to account for the cumulative effects. And also you want to be able to place the blame fairly. You want to have, you want to be able to compute what this impact is actually due to. So if the population is going to die anyway for other reasons, you surely shouldn't attribute that death or that extinction to an ecotoxicological insult. So why the population level? Well, if you're a chemist, you're probably most interested in the biochemistry of the thing, right? And that's got high tractability. It's easy to study chemistry comparatively, but it's got low environmental relevance, because you're not sure exactly, let's say you disrupted some pathway.
it's not perfectly clear what the impact of that disrupted pathway is going to be. On the other hand, you could say, no, I'm really interested in the whole ecosystem and how it's dynamically changing under this contamination. And that clearly has a lot of environmental relevance, but really low tractability. You really can't get there from here. It's not possible to do that sort of calculation. So what most people have done is sort of settle on the individual level contamination. So we expose animals and plants to concentrations of the bad stuff and see if they die or see if they have the diminished functionality in some way. But I think that what we would prefer is to go a little bit higher in environmental relevance, sacrificing a little bit in tractability, and that is to go to the population level. And I'll make arguments that why this is the right level to be doing ecosystem analysis. And of course, this contradicts what Jeffrey said in the first talk, when he said that he could do the whole ecosystem. Now, everybody knows that ecology is complicated, and it's also uncertain. And it's the case that for some species, if you reduce, say, juvenile survivorship by 10%, that could cause that species to go extinct. But other species, that kind of an impact might have no discernible effect at all at the population level. It might be, water off a duck's back, or impacts off a striped bass population. You could kill a lot of striped bass and have virtually no impact on the population because they're so fecund and stochastic anyway. And while it's complicated, it also synthesizes a whole bunch of things which could be quite variable themselves. So suppose you have some sort of contaminant which does cause fewer of the organisms to survive, right? There's a 10% decline in survival, but because of the way it works, it actually increases reproduction, and that's actually seen in some situations. And so you might ask, well, what's the overall effect of this sort of a contaminant? Is it a fertilizer? Are we helping the population, or is it a bad pollutant, pollutant bad thing situation because of the decline in survival? We need to be able to integrate these different kinds of impacts. So how do you integrate that? Well, ecological risk is really a combination of three sorts of questions. The first is, what's the species life history going to be doing? How does that species work, basically? The second is, what contaminants is it exposed to? What concentrations of contaminants is it exposed to? And how will those impact relevant life history parameters? And the third part is, of course, the uncertainty analysis or the variability analysis to sort of weld the life history information and the dose response profile together to form the ecological risk. And so how would that work? Well, ecological risk models, I argue, should be basically life history models. Life history just means, we take account of how animals or plants are making more of their selves. So you take into account the initial abundance, that is how many of the organisms there are. You want to take a modeling choice about what the time step is going to be, and then you estimate the survival rates of different categories of the organism and the fecundity or the reproduction rates. And maybe you estimate the dispersal rates and the variation in these various rates, all of which are called vital rates. And maybe you also include stuff like density dependence or carrying capacity, which is based on how the organism finds or makes its living in the world. That life history model is sort of the base case. It's the base information we have about a species, and it can vary with space, but often species are rather coherent. So striped bass in this location will be very similar to striped bass in another location, probably. And our ecological risks arise from impacts that are expressed through effects on any of these life history variables, right? So this is the life history of some, looks like a fish, right? So it lives for 5 years and then it starts to reproduce, and the adults live for maybe a long time, but they continue to reproduce at the same rate. So that's a typical life history of some sort of organism. It could be lots of things. And the mathematical model of such a life history is often expressed as this transition matrix model, where if you can see my mouse, that this vector here is the abundance of the babies, the abundance of the 2-year-olds, maybe. There are missing dots here. It should be ... And this is the abundance of the largest age class, say. And this is the top row of this matrix is the fecundities, or how many babies each of these classes make, so that when you multiply this matrix by this vector, that this row is multiplied respectively by this column, and they're summed up, and that gives you the abundance in next year's X1 class. And these guys are the survivorship, so they're multiplied respectively by each of these abundance categories to give you the abundance in the next age class or sage class.
¿Me traes acá? Tengo una conferencia.
If you have a question, maybe not. Okay. So these vital rates are, they're often sort of assumed to be constant for the sake of models, but of course in real life they're surely not constant, right? They're varying through time. And so if that's the case, then you apply that matrix model or whatever your demographic model is to a characterization of the population, and you find that, well, if you add up all the various classes into one total and call that the population size, then that population size is typically going to vary through time. And that varies according to the environmental stochasticity in the natural world, right? Sometimes it's a good year, sometimes it's a not so good year, but overall there will be a succession of ups and downs, and that's a possible future scenario for that population. Of course, that's not the only possible future. We don't predict the weather. We don't even know what the future is going to be in terms of good or bad years. So we can do another one with a different set of random variables. We'll get a different trajectory, right? In fact, we could do that many times and find all possible kinds of trajectories. And so you say, well, you can't really predict. Well, no, you can predict, but what you're predicting is not the individual trajectory. What you're predicting is this tangle of trajectories. The tangle is the prediction, right? So you see that, in the central tendency, it sort of tends to be going down, but every once in a while there's a chance that there's some increases. You can sort of look at that tangle as the thing that's being predicted in the ecological risk analysis. Any single trajectory might be the actual future, but the tangle as a whole is our prediction. And this approach acknowledges the natural variability in the ecological world, right? And this tangle then is decomposed into a risk language. So if the final population size after some time is, possible, a range of possible values with different probabilities, then the risk that some low population size happening can be estimated from this distribution here. So that's the risk language that we need to translate all our models into. And so that risk language actually has a bunch of different possibilities. You could talk about the risk of population decline. You could talk about the chance that it recovers. You could also talk about how long it takes the population to decline given the contamination profile that you see, or maybe how long it would take to recover given that you clean up that contamination. So a bunch of different risk analytic summaries, just to give you an idea of what I'm talking about here. So here's our tangle of trajectories that predicted the population's response to a contaminant. And we might look at the smallest population sizes for each trajectory. So if you look at the smallest value for each of those lines, those red bits are the smallest values of the y-axis that are observed. And from those, you can compute things like the chance that the population declines by some percentage, for instance. So this says the population is surely going to decline over some fixed time horizon. It's surely going to decline by a little bit, but it's very unlikely that it's going to decline all the way to extinction, right? 100% decline would be extinction. That's very unlikely. And you can compare this curve, which might be a base case, to an impacted case, right? You compare these two risk curves, right? This amount of risk happens just because the environment is variable, just because that, there are no guarantees if you're living in the outside world. Sometimes it could be bad futures, it could be a drought, it could be something weird happening. There are no guarantees. And so you have some risk, even if you don't have an impact. What's the attributable risk is the difference between the green and the red curves here. That's the risk with the impact is up here. And it's really only this amount that's attributable to the impact itself, right? This is already happening and would have happened even if there weren't an impact. You could also talk about the time the population takes to cross some threshold. So if you ask that question, then the X values here are the first time that a population fell to some threshold level, right? It looks like that threshold level is probably 50, whatever those units are. So if you look at the time outcomes from this ecological risk analysis, this probabilistic ecological risk analysis. You can summarize those with pictures that look kind of like this. This answers the question, how long does it take for the population, how long in years does it take for the population to decline to some critical size that you're worried about? Maybe that critical size is extinction, maybe it's, maybe you're worried about losing half the population or something. You can set what that threshold is, and this answers how quickly are you going to have to worry about it. And this says, for instance, 60 years, you're probably doing pretty good. Nothing bad's going to happen, at least for 60 years, and that gives you time to make up a better management scenario. And again, you would compare the base case with an impacted case, and only the increase in risk that's in this region between the two curves is the attributable risk that is indicting the impact. All right, so that's our risk language. That's how we would do it, how we would talk about the cumulative attributed risk. But I said at the beginning that ecology is complicated, right? So it turns out it's really complicated. So there are temporal lags. For instance, this is a real story from, looks like North Carolina, where there's this reservoir that somebody has put together, and there's a power plant right here, and it's putting ash, I guess it's coal fire, they're putting the ash from the power plant into the settling ponds here in this reservoir. And that's the ash then is leaching out the heavy metal selenium, and it's killing the bluegills that live in these settling ponds in this reservoir. And it's a horrible thing. Don't make me show you a picture of what selenium does to the bluegill. It's kind of disgusting. But it's killing the populations, wiping them out actually. And the public and the regulators are very upset about this. So what does the power company do? Well, they invested some money and they did some experiments, and they found out, oh, there's bluegill density dependence. And they found that bluegills are strange. They have this nonlinear, highly nonlinear density dependence. And we know that. So when we build the model, the demographic model, using those same techniques I talked about already, the projected recovery after the selenium is removed would look like this. It's in the first couple of years, it's going to grow and be at this high value. And then even without the selenium impact, it's going to crash. In 1 year, it's going to be like virtually zero. And then it's going to grow back again and do this cycling until it calms down. That's actually an artifact. It's a consequence of that density dependence, which is peculiar to the life history of those bluegill fish. That's called the Ricker density dependence model, in case you're familiar with that. This fact of growing exponentially and then crashing and then doing it again, turns out that's actually observed. It didn't take just 4 years, it took longer because this cleanup was slower than we thought, but they grew up and then had the predicted crash, just as we thought. So obviously, if we hadn't predicted that crash, the public would have been incensed, right? Because it would look like the population was doing well, and then obviously the evil power company did something horrible and destroyed the fish. So you better make sure you predicted that before it happened, because otherwise you'd be with bluegill egg on your face. So the other effects, like conflicting effects, this is another real story. It turns out it's General Electric contamination of ponds in Massachusetts with PCBs. And apparently it's associated with gross malformations and feminization of the frogs. Strangely though, so the gross malformations are causing declines in survivorship, but it's actually increasing larval survival. So the big fish are suffering and having fewer eggs, but the larvae actually survive better than they would without the PCB contamination. It may be because it's hurting some other species which is preying on them, and we don't really know why, but it does. And so you make a model of this particular system in Massachusetts, and we use a meta population, right? Different ponds are respectively distributed across the Massachusetts landscape, and they are informing each other. So we make a spatially explicit model. We model the dispersal and migration between the ponds. Sometimes it's complicated. And we also allow for local extinction. Sometimes a pond can wink out, or total extinction. And we ask the question, okay, so given these connections across space of these different populations and their respective life history structures, what do we expect in the overall population? And we can compute rather straightforwardly the risk attributable to the contaminant of PCBs from the General Electric plant. So it turns out that frogs live a risky life themselves, but the risk with impacts is still higher. In fact, because of the obvious individual level effects, the industry argued that, or despite the obvious individual level effects, the industry, GE, argued that the population's persistence in this area implies that it's healthy, right? It's still here. We've contaminated this site for 70 years and they're still living. And you would think that if you had what GE calls eco-imagination, in fact, an analysis suggests that those populations are a sink. So frogs come there and they die there and they don't reproduce, or at least they don't sustain themselves. Rather like the Ranger uranium facility, if the organisms were too dumb to leave, they'd just go there and then eventually die. There are also cumulative effects. So this is, there are 10 dams along a river, 2 power plants, various contaminants, and there are thermal effects and entrainment, impingement. That's when the animals are physically destroyed. And it's because the population lives all along there, they have all these different kinds of impacts. You have to accumulate them all, and it can be a messy business without doing the math. Finally, there are these indirect effects. This is starlings massing, and starlings sometimes do a lot of massing. These are normal populations. It turns out that they mass at power plants. They congregate at power plants because they're attracted by the warm concrete, and it creates a variety of problems for the people who run the power plant. So they try to control the starlings with an avicide, right? They use fenthion, and they coat these perches where the starlings roost or land with this fenthion, and then it kills them by poisoning them through their feet in just a few minutes, really. And in a month, you can kill 100,000 starlings easily. But unfortunately, the death takes several hours or days after the exposure to realize. So it turns out as a result, you've got a lot of poisoned but not quite dead starlings flying around. And the death throes of starlings attract predators. So you've got these kestrels and barred owls and snowy owls and great horned owls and coopers and red-tailed hawks, and they're swooping in, preying on these strangely acting starlings. And of course, the raptors are a lot more sensitive to the fenthion than the starlings are, and they just get walloped because they're accumulating a bunch of birds, and so they accumulate the poison. So that window between when symptoms emerge and when death emerges in the starlings creates this this problem for the raptors, the birds that we really like. And as a result, if you poison about 10,000 starlings a month, actually you poison untold numbers, but about 10,000 of them will survive and disperse around. Now, most aren't eaten, but some will be eaten, and their fenthion loads easily kill the raptors. And so the lab and field studies can't predict the population level effects on the raptors, right, the big birds, but ecological risk analysis can, and we can foretell how bad it's going to be for the snowy owl and so forth. And without it, we really couldn't tell. So this, for instance, is the with fenthion effects on the I think that's the Cooper's hawk. These indirect ecological effects kind of reverberate through these trophic chains, these food chains, right? So there are effects of reducing or increasing various populations have on each other, and also the toxicant biomagnification issues. So you might say, well, what we need to do is figure out the signed directed graphs that Jeffrey was talking about, right? So to model these ecosystems. And I would like to tell you that that's maybe easier said than done. It turns out that ecologists aren't really completely sure how these trophic interactions work. This, for instance, is the traditional model of predator-prey systems. It says if you measure, it's called prey dependence. If you measure prey as abundance of prey, and you ask, well, how much do predators consume in the form of prey per unit time, it'll be a function that looks like this. And that will imply certain things about this food chain. If, however, you measure prey according to the model called ratio dependence, then it's not prey abundance, it's rather abundance of prey per predator capita. So per capita in terms of predator. So how many prey items are running around for each predator, right? In that case, the model still looks like this, but the axis down here is radically different. It's a per capita abundance of prey rather than a just naked abundance of prey. And this difference, which maybe seems minor, generates completely different predictions about how trophic interactions are going to work, how these food chains are going to work. If you ask what most biologists believe, and I think this would apply to Jeffrey Dumbacher, he would believe that what's called the paradox of enrichment. If you increase the food for rabbits, you can end up crashing their predator populations, right? That's called the paradox of enrichment. And biologists believe that can happen, even though I would argue it probably doesn't. They also believe in complex equilibrium responses. I'll mention those in a minute. And it would also suggest if this prey dependence model is true, that there are more trophic levels, that is, the food chains are longer, involving more species in the tropics than in the north, and that dual extinction is impossible. Dual extinction is basically when the predators kill all their prey and then they starve, right? So both populations go extinct. The standard models, the models that Jeffrey was using, don't allow for dual extinction. But of course, we see dual extinction in the lab and in the field as well, even though it's theoretically not possible. Also, the prediction of the standard models that the tropics will have more links in the food chain turns out to be wrong. I mean, in the tropics, the food chains are about the same length that they are in the Arctic. We thought for a long time they were different, but inspection sort of tells us otherwise. And most interestingly, when the productivity increases, if you somehow increase the amount of food, then different models sort of tell very different stories about what's possible. In Lagoons models, of course, you could get cycles. And in prey-dependent models, you could get cycles or possibly extinction. But in ratio-dependent models, you'll really just get damped cycles. They won't be cycles that'll equilibrate. So, for instance, if you change the prey growth rate because you increase its food from low to high, then the standard model might say, well, it was stable before, it might go extinct. The predator might rather. In this case of ratio-dependent model, it would say, well, if it's low, you might have dual extinction, but it's going to be stable if you have enough productivity, right? So radically different sort of theoretical expectations. And here's, I think, putting a point on it. So remember when Jeffrey was talking about his positive and negative impacts, if you change the, if you increase the productivity in a system, you have, better food or better exposure to nutrients, something like that. How that impact will go up the food chain sort of depends on which trophic level you happen to be in. So predators up here see one thing, but then as you go down, the signs can vary. In the ratio-dependent model, if you increase the basic productivity, everybody actually goes up. It's not complicated like Jeffrey would suggest, and the standard models would suggest. So, for instance, again, if you increase productivity, everybody goes up in the ratio-dependent models. In the prey-dependent models, it matters which level you're at, whether you go up, or you go down, or you stay the same in this complicated way, depending on which level you are in the food chain. So I would argue that prediction doesn't actually exist. So I think it's fair to say that ratio dependence is by no means the accepted model in ecology, and yet it's, well, probably my friends say it's true. It's probably true, and yet it's completely outside of the standard Lotka-Volterra style models. And so if it's the case that ecologists can't even decide how the basic predator-prey equation should work, then I would argue that ecology is really pre-scientific. It's certainly too immature to support an engineering based on it, right? Even food chain models are controversial. And if you get to be what you would call a real ecosystem model. I mean, I'm very suspicious of those. It's really just put together with a lot of assumptions, and maybe not a lot of really respectable theory. Now, I'm talking now about food chain models. Competition models are simpler, right? If their species are just competing with one another, like Jeffrey's first example this morning, maybe that's a simpler model. Maybe that's something that can be done. But certainly the things that include even the food chain are pretty complicated, and maybe arguably beyond us at this point, at least as a discipline. I don't think it's fair to say that we know what we're doing yet. Ecology is pre-scientific, and yet it's clear that ecology matters a lot. We can see the temporal lagged effects, the conflicting effects, where it's good or bad. We don't know which is going to end up. We have to accumulate impacts. We have compensatory phenomena like the bluegill that seems to do different things based on what abundance they're at, the indirect effects, and other weird counterintuitive effects, such as, for instance, when you kill some of the organisms and the population as a whole does better. That's also easily shown in many situations. So my conclusions are, people, some people at least, can't get very excited about what I call sad lettuce seedlings. So a lot of toxicologists use lettuce seedlings to measure toxicity of some contaminant, and if the lettuce seedling dies or is deformed or something, then that's a bad toxicant. But obviously that's going to be a hard sell to explain that to the average American Republican, for instance. They're not going to be worried too much about the lettuce seedlings. But they sometimes care about ecosystems, but really only if they're economically important. Unfortunately, we can't really make good predictions about entire ecosystems, but I think what we can do, at least pretty well, I think, is make forecasts about impacts on whole populations. And if those are resource species or species that they're interested in, like threatened or endangered species, maybe that's making a more relevant case, a more compelling case. And we can make predictions about populations at that level. It's really, I talked about the transition matrix and the life history parameters. It's really just accounting, but it has to be probabilistic to tease out what those attributable impacts, the things that we can blame on the contaminant, and not just the fact that we live in a variable world. So as I said at the beginning, these are my conclusions, really, that that we should focus on the population level, not individuals and not whole systems. We should look at express things in a risk language. That's the language of engineering, and we should look for the cumulative attributable effects. So here's my thanks, including Dominic Pillay. Look, see here at the top of the list. So those are the thanks, and these are some acknowledgements. Eco-imagination is a service mark of General Electric, which I found very amusing. Am I wholly over time?
No, you're not too bad. Thank you very much for your talk. Do we have any questions for Scott then?
See, I never have questions. Nobody ever has questions about the talks.
May I?
Sure.
Or comments?
Can you hear me, Francis? Yeah.
Yeah, we can hear you.
So, Scott, you talked about the effect on a population level, rather the effects at an individual level. When we are performing ecotoxicological tests, we are working with individual effects.
Right.
But when we are thinking on prognostic risk assessment, bioassays,
Right.
It is a prognostic risk assessment. We are not working with a real situation. When I work with a real situation, we are working with biomonitoring, right? So in biomonitoring, you can get some ecological indicators in order to feed your
Right.
risk assessment.
Right.
For example, abundance of a given organism,
Right.
and then we can correlate the abundance
Sure.
with the concentration of a given metal, of a given microplastics, or whatever.
Right. Right.
So it is.
So you're
possible.
talking about
Biomonitoring.
biomonitoring. So you're measuring the species or whatever it is, monitoring it in real time, and that's the species of interest, right? That's the
Yes.
indicator species.
Yes.
Okay, sure.
But at a laboratorial scale, So there are some possibilities to do it, but as I said to you before, the terrestrial model ecosystems. So at the laboratory, you can simulate an ecosystems with many populations, and then you can see the interactions
In the laboratory, you're saying.
at the laboratory.
Right.
You can, for example, with soils, we have a core of soils, and we can contaminate this core of soil with a given contaminant.
Sure.
And then we put there so many populations of earthworms, mites,
Right. In
envelopes.
the soil ecosystem.
Yes.
Yeah, sure.
And then you can simulate a soil ecosystems disturbed by a given contaminant.
Sure.
And then you can see the interactions between the populations and the effects at a population level. So it's possible.
Well, yeah,
And then you
I'm not saying it's impossible. I'm saying it's hard to do.
yes,
And
of
it's
course,
especially
yeah,
hard to
yes, yes.
extrapolate to species that, you know, my Republican friends care about, right? So earthworm populations, even whole assemblages with many species in the soil biota. I mean, you are interested in them. I am interested in them. I think, you know, anybody would be interested in them if they thought for 10 minutes about it. But we're talking about people who are, you know, in control of the money and in control of the decision-making process. When are they going to get motivated to change? Well, you know, it's a harder sell to, you know, say, oh, the soil biota is in trouble.
Yes.
Even if it's terrible trouble, right? If you could lose all the nematodes in a soil biota, right? That would be a devastating effect, I'm sure. But what does that mean to organisms that, you know, what's it mean to humans? What's it mean to threatened and endangered species that are given special protection under the law? Or more importantly, what's it mean to the cows that graze on this land? Because that's really the only thing they're interested in. That's a harder sell.
In terms of human interest, we are going to we need to define which losses are acceptable in terms of
For
ecosystems.
humans?
No, for example, it is impossible to protect the entire ecosystem.
Right,
It is-
right.
This is impossible.
Sure,
So
sure.
we should define which ecological losses are acceptable.
Sure, sure. I totally
uh,
agree. But the secret, it seems to me, is having some language which is consistent and meaningfully exchangeable from site to site. So, you know, one site, the species at this site don't even appear, you know, there's a site in Maine that's contaminated, it's got frogs and, you know, trees and stuff, and it's totally different from the site in Florida, right? So how do you trade off Maine populations against Florida populations? It's not an easy,
Yes.
it's not easy at all, right?
Yeah.
and especially if it's just, you know, naked toxicity, sometimes at the tissue level, that's a really hard, it's hard to project, right? And given the complexity that ecological systems exhibit, even just these ridiculous simple examples, which everybody acknowledges are all true, right? Even that complexity is quite hard to, you know, to bring into one model to take account of all of that.
Yeah.
And yet that's
I
what we
agree,
need
I
to
agree.
do.
Yeah,
It's what we need to do. And we just have to figure out, you know, the machinery to get that all in so that we can start to make those trade-offs, because we will be making trade-offs between, you know, different species and different sites. We sort of have to, because, well, we're doing it now. We're just doing it in an unconscious way. It's whoever can scream loudest. You know, if the Floridians are screaming louder than the Mainers, then they'll get more money. And that doesn't seem fair.
And so so you work with fish, right?
Yeah,
You have been working with fish.
computers. I work
Yeah.
with computers.
So I can show you another a tool that we can use for fish. So at a population level, it is possible to by using the pre-probit analysis. Have you ever?
Pre-probit?
Yes, pre-probit analysis.
Probit.
Yes.
Oh yeah, sure.
You can estimate the concentrations of
Right.
a given contaminant at a population level
Right.
that can kill
Right, sure.
50% of the population,
Sure.
not at an individual level.
Right.
So in my next presentation, I'm going to show some doses of a given contaminant that can kill 50% of my earthworms, of my collembolas, but at an individual level, okay?
Right.
But it is possible for fish to estimate at a population level the concentrations the time required, the time of exposure, which is required for that population
Right.
to reach the concentration, which is able to kill 50% of that population.
So,
I made that for alligators. For
right.
Brazilian
There are a
alligators.
variety of techniques which are trying to get to the population level, like LD50s,
Yes.
lethal dose 50s or lethal concentrations 50s, or any lethal dose anything, right? And as well as not just LD50s, but also the species distributions that Jeffrey was showing earlier, where different species are differentially sensitive to different concentrations, right? And they either, if it's this concentration, then some number of the species will be blanked out. If it's higher, more of them will be blanked out. Those species distributions are that same idea, only not not going from the individual level to the population, but rather now from the species to the assemblage of species level or the ecosystem level. So all those ideas are clearly part of the story, and we're clawing our way, trying to get to the ecosystem relevant. We want to that relevant stuff, and we also need it to be tractable, so we can actually work with it and do it with enough, because the job of the the chemist or the biochemist, the toxicologist, to figure out what those toxic effects are is already hard enough, right? It was just, if you could, the step I think is needed is to translate those into population dynamic vital rates. If you can do that,
That's a challenge.
it's a challenge.
That's a challenge.
But it's something that I think can be done. And when it's done, then certain things just become easy. Not everything, but certain things become easy at that point. So, yeah. Are we past time now? I don't have a clock.
We are, but we have quite a bit of buffer, including the open discussion and ending at 3. So our final talk will be Ricardo. So I don't know whether there's any last final comments or questions for Scott, because we do have an extra 5 minutes, I reckon.
So we're good.
And if not, let's wrap up with Scott and give him a round of applause.
No, we didn't applaud the others. No, we don't do that.
Okay, no round of applause.
Let's see.
So maybe you want to start sharing Ricardo's slides.
I think. Have you opened it yet, Ricardo? Well, open. So maybe browse.
This one.
Okay, great.
May I sit down here?
Yeah.
Yes. So good morning, everyone. Well, now I'm going to present you the work, land disposal of metal-contaminated dredged sediments and their ecotoxicological risks to soil biota. So this presentation is strongly related to my last presentation. So it doesn't work.
Click on the display screen.
Oops, yes. So over the last decades, the expansion of urban areas has increased the discharge of domestic sewage, industrial waste, and garbage to tropical estuaries, fluvial systems, and lagoon systems, causing the contamination, eutrophication, and silting processes of these ecosystems, and also compromising important ecosystem services. The situation is especially dramatic in the Rio de Janeiro state, where lagoon systems in Guanabara Bay and Sepetiba Bay are strongly impacted, and their bottom sediments need to be urgently dredged. So here we have some aspects that should be considered when dredging sediments from aquatic systems. First of all, when a sediment is dredged, we have the resuspension of the sediment in the water column, thus increasing potential bioavailability of contaminants and increasing the generation of toxic gases, especially in very eutrophic environments and very eutrophic ecosystem impacted by domestic sewage. Such toxic gases can include methane and ammonia, which are very toxic. The disposal of dredged sediments in terrestrial systems can cause serious adverse effects on soil biota. Human populations, when exposed to these materials, can also be at risk. The weathering of soil sediment mixtures can also contaminate groundwater, and leaching and erosion processes on soil sediment mixtures can also mobilize contaminants to aquatic ecosystems, then contaminate the aquatic biota, and human populations whose diet is based on this contaminated aquatic biota can be also at risk. So the Brazilian legislation for dredged sediment disposal in soils and aquatic environments, they are strongly based on guidelines idealized for temperate ecosystems. And because of that, they do not reflect the specific properties of tropical systems. This kind of guideline has supported the management of environmental costs of dredging interventions in Brazil. For example, the dredging of the Jacarepaguá Lagoon system in Rio de Janeiro city was estimated in $200,000. So we need better guidelines. We need guidelines that are appropriate to tropical systems in order for a better management of these costs. And also take into consideration a sea level scenario. Bottom sediments from fluvial and estuarine systems need to be dredged to increase the capacity of water storage in rivers and estuaries, and to prevent huge inundation events. So taking into consideration the current reality, the near future, the increase of human populations, the search for new areas for human habitation, the sea level rising, all these contexts require new appreciations of dredged sediments, and not only a simple comparison with a legislations idealized for temperate ecosystems. All this scenario requires a balance of risk and environmental costs that should be based on geochemical, ecological, and toxicological processes in order to generate sustainability indicators for disposing dredged sediments in tropical soils. Most of geoenvironmental studies focus on soil contaminations. They are, again, strongly based on total chemical analysis, metal speciation, and metal sequence extractions. Even though these approaches are very important, they are not able to evaluate some synergic effects of contaminants and ecological damages. Earthworms, collembolas, mites, and some vegetables are commonly used as test organisms in ecotoxicological tests, and the use of such organisms in bioassays are due to their ecological relevance, short life cycle, and simple cultivation at the laboratory. So here, I'm going to show you some results related to the evaluation of potential toxicity levels associated with the disposal of dredged sediments in tropical soils. Take into account two study cases, the Guanabara Bay and Rodrigo de Freitas Lagoon, both in Rio de Janeiro city. The first study case is the Guanabara Bay. I'm going to present some results that are already published in this paper here, in the Environmental Science and Pollution Research journal. At the Guanabara Bay, here we have the Rio de Janeiro city. Here in the Guanabara Bay, we have 5 sampling sites for studying the toxicity of dredged sediments. Here, I'm going to present you some results of the port of the Rio de Janeiro and port of Niterói. We performed the sampling of the sediments in the winter and in the summer in order to evaluate potential seasonal differences in terms of toxicity. To simulate terrestrial disposal of dredged sediments, we mixed the sediments with a typical tropical soil, which are the feral soils. The feral soils are typical tropical soils. They are widely distributed in the Brazilian territory. They are very acid materials and then have low fertility levels. And most of the minerals that compose these soils are kaolinite, gibbsite, and goethite. So this is a typical tropical soil. So to simulate terrestrial disposal of dredged sediments in soil, we mixed the sediment with a feral soil sample in order to obtain the following doses. 0 dose was the poor soil, and 30% was the highest dose applied on the soils. We determined total metal concentrations in the dredged sediments, and we compared such concentrations to the limits established by Brazilian law for dredged sediment disposal. And also we determined total organic carbon contents in the sediments. Here I'm going to show you a geochemical index that we use to evaluate the metal contamination levels. This is the geoaccumulation index. With this index, it is possible to compare the concentration found in the field with the concentration considered for a given local background of a given metal. So here we can classify the sample into 7 classes, from 0, which is practically non-polluted, and 6 with the highest level of pollution, which is very, very strongly polluted. In this case, we use the acute toxicity test with earthworms, Eisene and Andrei. The test consisted of 4 replicates containing 500 grams of soil. The moisture content of the soil was adjusted according to the water holding capacity of the soil. We used 10 adult earthworms with well-developed clitellum per replicate, and the earthworms had similar weight. The test duration is 14 days, and the test was run under constant illumination and controlled temperature. By the end of the test, we can evaluate the mortality levels of the organisms and possible biomass variation of the surviving organisms. And the dose of sediments, which was able to cause the death of 50% of the organisms, was estimated using the probit analysis. So here we have an adult earthworm with a well-developed clitellum. So here we have the earthworm cultivation at our laboratory, the earthworm collecting, washing, earthworm being waiting after being dried, and the inoculation of earthworms to the soil. So here we have some results related to the port of Rio de Janeiro. Here in yellow, we have the limits established by Brazilian law for dredged sediment disposal in aquatic environment. So we have level 1 and level 2. Level 1 means low probability of adverse effects on aquatic biota, and level 2 means high probability of adverse effects on biota. This is for dredged sediment disposal in aquatic environment. And here we have the limits for soil quality. So the prevention limit is the limit is the limit that we can expect harmful effects on soil ecological receptors. Here we have the concentrations of our metals in summer and in the winter, and except for cadmium and arsenium, all the metals analyzed in this study had concentrations above the limit established for dredged sediment disposal in soils and in aquatic environments. Here we can see that winter concentrations were higher than the summer ones. So in the winter we have our worst scenario. So in the winter we have less water in the system, so the contaminants tend to be more concentrated in the water column, and then they tend to precipitate to the sediments, to the bottom sediments with salts. So that's why winter sediments are usually more contaminated compared to the summer ones. Here we have the metal concentration in the port of Niterói. In the port of Niterói, metal concentrations were a little bit lower compared to the port of Rio de Janeiro. Here our problems are zinc, copper, and lead. Zinc and copper are good indicators of domestic sewage, so most probably this zinc and this copper come from domestic sewage, even though other sources cannot be ignored. Again, the concentration found in the winter were higher than those found in the summer. So in the winter, the contaminants are more concentrated in the water column and tend to precipitate to bottom sediments. Here we have the results related to geoaccumulation index, where we could classify the samples into different levels of contaminations. So zinc and copper had the highest level of contamination, so very strongly polluted, and strongly polluted to very strongly polluted. The lead pollution levels were also very high, but nickel and chromium concentrations were not so relevant, and most of them were classified as no pollution. But here we have the results related to the ecotoxicological test with earthworms in the port of Rio de Janeiro. Here in these gray columns, we have the survival in percentage, as surviving organisms in percentage. And we can see here that winter, the winter sediment were more toxic to the earthworms compared to the summer ones. For example, here in this dose in 18%, we have more than 80% of the earthworms that are still alive. And here, all the earthworms are already dead. The LC 50% value was estimated in 7.7 for summer and 19.6 for winter. So here, survival and biomass here. Okay, so the gray columns are survival. Okay, and this one here are the biomass.
Can they be over 100?
Hmm?
Can they be over 100?
Is the standard deviation? Yes, but the absolute number, no. Here we can see some increase of biomass levels of the earthworms, some biomass. So here, earthworms increased their biomass. We believe that it's due to the absorption of salts. What? Or maybe that's another hypothesis. Maybe they can recognize the organic matter for sewage as a food source. Yes, but another probable hypothesis is also that such earthworm can absorb salts, and then for maintain the osmotic equilibrium, then can absorb. So here we not have a real mass accumulation. We have water accumulation. That's another hypothesis, or all the hypotheses can occur at the same time. And the concentration of hormones are also very high in these sediments because they are highly impacted by domestic sewage. So there are many hypotheses for this increase of biomass levels for the earth forms. So here we have the ecotoxicological evaluation of the sediment of the port of Niterói. So again, the sample collected in the winter were more toxic compared to the summer ones. But here we didn't have a great variation of the biomasses losses for at least in the summer. And the toxicity levels found in the port of Niterói was lower compared to the Rio de Janeiro, to the port of Rio de Janeiro. Here we're gonna see the results obtained in the Rodrigo de Freitas lagoon. Some of these results are already published in this paper here, and I'm gonna also use some results published in this another paper with the same sediment, with the same dredged sediment sample. So here we have again our Rodrigo de Freitas lagoon, here Leblon Beach, Ipanema Beach, and here Copacabana Beach. These are our sampling point, our sediment sampling points. We mixed the samples collected in each sampling point in order to have a composite sample which is spatially representative of the entire lagoon. And this is our dredged sediment sample. So it is a composite sample formed from the mixture of different sampling points in the Rodrigo de Freitas lagoon. Our dredged sediment sample, our composite sample, was mixed with the ferrule soil, the same soil that we used for the Guanabara Bay, but also we mixed our sediment sample with the Cherno soils, whose properties are the opposite to the ferrule soil. So and then we are going to see that we are going to have different results according to the soil type. Here we have metal concentrations in the dredged sediments, and the only concentration that was above the limit defined by Brazilian legislation was lead. The other metals were in agreement with the Brazilian legislation for dredged sediment disposal in soil. Here we have the results relate to the ecotoxicological evaluation using earthworms. Here, the ferrule mixture, and here the Cherno soil mixture. So with two different kinds of soils. And the toxicity levels in ferrule soil mixture tend to be higher compared to the Cherno soil mixture. This is probably because the Cherno soil have a specific type of clay, is this expensive clays, which are able to absorb metals and other contaminants. And because of that, the Cherno soil mixtures generally have lower levels of toxicity compared to ferrule soil one. So soil properties can play a crucial role in the toxicity that we can observe in the test. So when disposing these sediments on terrestrial systems, we have to verify which type of soil is there. So this is very important for you to plan the right places to dispose dredged sediment and other wastes. So here we have a comparison of LC 50% values obtained in Rodrigo de Freitas Lagoon and other values obtained in other estuaries along the Rio de Janeiro state, and even compared to other areas in the Rio de Janeiro state, our sediment of the Rodrigo de Freitas Lagoon can be considered very toxic, even compared, for example, to the sediments collected in the Septiba Bay or the sediment of Port of Niterói. Besides the acute test with earthworms, we also perform avoidance tests with earthworms. The test duration is only 2 days. Our testing systems is composed of 2 econ compartments containing a control sample, non-contaminated soil, and a test sample. So here we have a control soil, and here we have a contaminated soil. Then 10 adult earthworms are inoculated on the interface of the soils here. And after 2 days of exposure under cycles of light and darkness and control temperature, we can analyze which compartment the earthworms preferred. Or so from this assumption, we can evaluate avoidance responses of the organism. Sometimes the organisms are still alive. They can still have a good reproduction, but sometimes if they can, if there is the possibility, they can avoid the soil. So these test doses that we use for the avoidance tests were those that were not able to cause the death of the organisms. So even though those doses here, for example, 3% dose, even though these doses were not able to cause the death of the organisms, they were able to cause significant behavioral effects, avoidance responses on the organisms. This line here, this dashed line here means the limit for the habitat function of the soil. So when we have more than 80% of avoidance responses, we can say that the soil as habitat is already limited, at least for earthworms. We also perform the reproduction tests with collembolas, which are soil arthropods. The test duration is 18 days. The test was run with 5 replicates of 13 grams of soils and 10 adult organisms per replicate. The soil moisture was adjusted according to water holding capacity, and the test was run under controlled temperature and cycles of light and darkness. And by the end of the test, we can evaluate adult mortality and reproduction through the number of juvenile organisms. So here we have the results related to the reproduction test with collembolas, Folsomia candida collembolas. Here in these columns, we have the number of juvenile organisms in feral soil mixtures and internal soil mixtures. Internal soil mixture, we have an increase of juvenile organisms compared to the control sample. Well, most probably, this dose of sediment was not toxic to the organisms, and maybe the organism could recognize organic matter from domestic sewage as a source of energy, and because of that, they increased their reproduction levels. This is a hypothesis. In the feral soil mixture, we have a very clear dose response. With those increasing, we have the decreasing, the reduction of the reproduction from this dose, from 5% in both soils. So final recommendation for further studies is the mapping of potential toxicity in other estuaries and rivers. of the Rio de Janeiro state to have an inventory of potential ecological risks related to dredged sediment disposal in soils, identifying critical areas in the Rio de Janeiro to be prioritized in further dredging interventions, testing dredged sediments with other types of soils, since soil properties can play a crucial role in the toxicity and metal bioavailability, metal bioavailability levels. We also want to test dredged sediment with other soil organisms, such as mites, lettuce, and micro earthworms, the enchytrates that we say, micro earthworms. And also, we want to study the possibility of using dredged sediments as an input in the agriculture and beach nourishment, based on the results of the ecotoxicological tests. So these are my contacts, and thank you for your attention.
Thank you very much, Ricardo. Do we have any questions at all from the audience?
Yeah. So I guess we're talking about terrestrial disposal because
Yes,
you can't do oceanic anymore, right? Oceanic
We
is
can't.
illegal. You
no,
can.
we can.
So why don't you just send it out to sea?
No, usually they search for caves into the ocean.
Oh, really?
Yes.
Didn't know that.
But they try to do it for when they perform the dredging of sediments of the Guanabara Bay for the Olympics.
Right.
They tried to put the sediments on the ocean, but they didn't plan very well, and the dredged sediments reached some beach of the Rio de Janeiro.
They what?
Uh,
The beach. Oh, really?
yes.
That's embarrassing. And open ocean is like 12 miles out. Is that illegal under international law now?
There are some requirements that we should check to perform. But you can do it. It's not.
Okay.
It is allowed. It's not.
So, several questions.
But terrestrial disposal of dredged sediment is also very common.
Yeah.
Unfortunately,
Yeah. So you said it, but I missed it. Why are the winter and summer metal concentrations different? I don't understand.
because in winter is our dry season. So during the winter we have less water in the systems. So
So it's literally less water, so the concentration goes up. Okay,
Yes.
it's saltier. So I guess that's. So, I mean, there are a couple weird things. I mean,
such as
well, I mean, I'm sure those hammers were different hammers. That was very disturbing to me. They were there for
where, Scott?
for scale. On the pictures for scale, there were two hammers, right, on one scale, and they were clearly different hammers. So
Which ones?
I don't back further. It's obviously trivia. Yeah, there we go. Those are different hammers, right? Am I losing my mind? Of course they're different.
Yes.
Like these aren't the same scale. Okay, so but that wasn't the. Okay. The ferrosol and the charnosol. Oh, okay, now I remember the question.
Mhm.
You said that it was clearly important that we know where we're putting it, what kind of soil it's there. I assume ferra and ferrosol is lots of iron, right? That's red.
This is the most common soil in Brazil.
And that's because of the iron content, is that right? And I never took pedology. So what's chernosoil?
Cherno soil is a typical soil of temperate environment and subtropical regions.
So what's
They are widely used in the agriculture because the fertility levels.
they're rich. They're the rich
Yes,
loamy
yes.
soil. Okay.
They are the opposite of the ferrosols. The ferrosols have low levels of fertility. They
Right.
are very acid,
Right.
and the
okay, I
chernosols
see.
are the opposite.
Right. So when you said that we need to distinguish where we're putting it, you were drawing on the. Could we go to that figure?
So in this case, the difference were not so huge.
Oh, okay.
but-
That's what I wanted to hear. I'm going, I don't see any difference.
Yeah, no,
Okay,
no,
good.
yes,
But in general,
but
that's the
yes,
case. Okay,
yes,
sure.
yes.
And do you have a lot of Cherno soils down there?
In southern Brazil, yes,
Southern Brazil, sure, okay.
and in Rio de Janeiro we have a small area with terms.
Yeah. Okay. Well, thanks. Those are really my questions. But I think for the discussion, I would like to, and this is why we dragged Dominic over too. I'm really interested in the IGO, the Metal Geoaccumulation Index. And this problem, I mean, it's a problem across science, right? We have this, when we're struggling to go from a sort of observatory, sort of life, sort of observatory phase to a predictive phase of science, you want to develop these indices so that you can understand what's happening, right? That's the natural thing to do. It's not quite modeling, but it's sort of an associational connection between, what you can see and what you can expect to see based on history. And clearly we have these, I mean, Mike Bather, for instance, talks about wood products getting different grades. So if it's got lots of knots in it, I guess it gets a low grade. But the reproducibility of the features of this scheme that he uses to grade the woods are not very strong, right? He's looking to make a better, more scientific strategy rather than just this index, right? And in medicine, these indices arise all the time. Biologists are famous for their indices. They figure out, there's something going on here. I'm worried about this, and these look like states that are leading to that bad outcome. And so I'm going to make an index along the scale from the really good to the acceptable to the not so good to the terrible.
In terms of soil or sediment contamination, the problems of this geochemical index is that they only take into consideration abiotic data.
Okay.
So we need some index that can integrate ecological data and geochemical data. So in this index, we only compare the concentration, metal concentration in the sediments and metal concentration in a background sample. So we compare the natural concentration that should be expected for a given environment and the concentration obtained in the fields at a logarithmical scale. This is for segments.
Right. Well, I guess, again, I'm being highly presumptuous and maybe pretentious. And, like any good mathematical biologist, I'll have a bit of physics envy when I start talking about Newton at this point, right? So Newton came along and said, yeah, motion of bodies, we got to figure out a theory for the motion of bodies. And there were a lot of systems around that he could have used, but he picked one that was almost weird because it didn't include any of these important features about bodies other than their mass. Just this weird thing. Why mass? I mean, clearly the size of it matters and how it's shaped matters. And of course, those things do matter in fact, right? But he ignored those things and said, it doesn't matter. I only look at mass. And obviously a lot of things that people might agree don't matter, but color and, temperature, how do you know those don't affect, right? And ecologists, seems to me, we're sort of pre-Newton in the sense that we don't really know what the variables are yet. So we're sort of, all the variables that we can possibly measure, we're throwing into the basket and sort of shaking it around and looking for associations, which are the variables that seem to be on some gradient between good and bad.
Many possibilities.
Yeah. And so do you have, I mean, where do you think this IGO, for instance, Mueller 79, you said it's abiotic, but I mean, is it a good scheme? I mean, is it as good as, say, Mike Bather's wood grades or a medical doctor's index for your heart health based on, his 30 years of experience with hearts of people like you and their outcomes, whether they lived or died? He's got a plot, he's got some data, and he's built up this index that he says is useful. How do we know if it's useful? How can we check if it's useful? And how do we know that we shouldn't be throwing out most of it and just keeping the part that corresponds to the mass, in the Newtonian model, the thing that really matters? How do we know any of that?
I understand your point of view.
I just don't like it.
But no. But I think it depends on the response that we are looking for. For in this index, we are only saying that the concentration is significantly higher than the natural concentrations.
Measurably higher.
Yes, but the ecological meaning of those anomalies,
We're not sure.
yes. And even a result like this, for example, that we have all the and that we have, for example, almost 40% of the earthworms were died. What are
They were
the
what? Died,
Here-
that they died?
yes?
Oh, okay, yeah.
Yes, and 40% of the earthworms were died, almost. What is the ecological relevance of such results?
Right.
Here we
Yeah, I was
have
curious, you said
at an
80
individual level.
Yeah, yeah. Well, you said, actually, you said as a throwaway almost that in the avoidance experiment that it was below 80%
Yes, the soil has as habitat.
was no good. So how do you
yes.
know that? Is that that's an
This
arbitrary?
is a
line?
guideline from established by ISO,
Oh, okay, okay.
and we use
So I think it's
that for
Okay.
for Columbus, the limit is 70% of avoidance responses.
okay.
I got a-
Clearly, that's just arbitrary. Somebody had to have did it
Yes,
somewhere.
yes,
Okay,
yes, yes, yes,
okay,
yes.
that's very interesting.
Well, if the earthworms avoid the soil, they
Sure.
in fact they do not recognize the soil as a
It's a
habitat.
habitat, sure. Okay. Well, thanks.
Oh, thank you, Scott.
Done.
So
No questions? So you you look like you're under oath there.
Sorry, do we have any more questions from your side, Scott? Or if there's anyone from the Zoom chat as well that would like to ask a question, you're more than welcome to unmute yourselves.
I noticed that, oh, what's the little, in that worm pornography that you had, the little band, what's the name of that band? On the
Clitellum,
What is it?
clitellum.
Glidellum. What is that? Is it reproductive bit?
Yes,
I knew it was porn. Yeah,
they have both female and male.
Right,
Yes,
right.
yes.
it's a party. Porn
Yes.
time.
And Columbulum have parthenogenetic
Oh, Columbus
reproduction.
Zoo?
Yes.
Oh, really? I didn't know that.
Parthenogenetic reproduction. Yes.
Really?
Yeah.
Do other copepods, are they?
They are only female organisms for Columbus. They are parthenogenetic.
Oh, in general. for
Yes.
Columbus. Oh, I didn't know that.
So is it clear how you're interfacing the other stuff with the model now?
I cannot hear you, sir.
Is there any ideas coming out how to interface, so how to expand some of the stuff to the model?
Yeah, so I was talking to Scott about the possibility of numerically integrate ecotoxicological data, physical data, chemical data, and metal data in order to have one number. Yes.
Okay.
So for you to do this, you need to define some criteria. And the definition of these criteria are really, really complicated, but it is possible. It is possible.
It's actually quite similar to the kind of things that you're talking about with respect to the dam safety as a function of vulnerability. You're creating a scale from something that's clearly not good to something that's clearly much better, and then trying to.
So you just so you've got like the whatever you said 4 or 5 axes, and you just make some of those axes. Is that right? There's some of the mass thing. Is that what we're talking about?
Well, that was the question for lunch.
Actually, I have so many data
Right.
means
for
variables.
different sampling points. I have
Oh, do you mean spatially integrated?
yes.
So you want like some map of it? Oh, we can do
Yeah.
that. That's not too good. So do you have like?
So
all
now,
the
I say
data-
at this moment, my idea is a binary, 0 and 1, 0 and 1 indexes. but I would like to use something more numerical, you know.
Okay, you want something a little bit richer. You want to
So-
be able to express more in it.
Yes,
than
yes.
two outcomes.
That's why I would like to show you,
Sure, let's have a
because
look at the data.
perhaps
yeah,
you can
yeah, yeah,
we can
let's have a
help,
look at the data.
and then we can do something together.
So definitely, if you've got experiment here, experiment here, experiment here, experiment in space, and you've got some values associated with those experiments. Do we have like time there as well, or is it just like you just do it once in each location?
Yeah, for each I have performed ecotoxicological tests for each sample.
Okay, and that's all around the dam site, right?
Yes,
And so, and this is after the failure.
after the
And so what does the geographical reference look like? How do you know where you were? Like, so is that like a latitude and longitude, or?
yes.
Right, so you've got a latitude and longitude, you've got some measurements. And we know from what happened with the Bromotinia, we know where the waste went. So we could work out like the distance that you measured from the dam site, right? And then we can do a regression to come up with some risk function of each of those variables to get at least what we expect the concentration to be. And that's actually just a univariate problem, right? I guess, well, we just start with the univariate problem. So we just do distance from the dam distance from the dam failure site. That's easy because it's a point. Distance from the dam. But I guess distance from the waste is the more relevant one. So distance from the waste. Did you actually measure the waste as well?
Yes.
So yeah, we can definitely do that. That seems.
So did we explain to the recording that what we're talking about is terrestrial exposures to mine tailings that have occurred because of a dam failure?
Sure. So now 2:30.
Okay.
So you've got that data with you?
Yes.
Can we have a look at it?
Yes. Now here.
Yeah. Why not?
But not here in my computer. Not here.
Yeah, not yet. So you're not excited about this problem of the index, I gather.
I don't think I understand what the problem. I mean, if it's just we want to put classes, like we just want to group things together in severity, I don't really get what the index is about. I don't get what it tells us.
Well, it's a guess. I mean, why I think it's important is because we have the same problem in medicine. We have it in engineering. We have it in this.
How bad is bad?
Yeah, especially
But
since
how bad is bad? We
need to know how massive it is without understanding that what it is we need to measure to figure out mass, right? Or
well, I mean, understanding about the variability between like the interaction between the things, because it might be just they're all linearly related, right? If the amount is bigger, then the consequences are bigger or whatever.
the problem is that if you had data, and nobody has the data that would be required, but if you had the data and sufficiently much of it, you could construct a regression analysis, and you could determine, which variables were important to include, and you could sort of throw out some variables and maybe keep in the important variables, and just see, and of course it would never be predictive necessarily, because some things, it's like trying to do medicine, or it's like trying to do nutrition science by.
I think what Ricardo's
But
talking
without
about,
all the
there were some
information.
parameters that I exclude for the analysis because they were not significant to toxicity, and then I excluded them from the analysis. So I have to
How
show
did you know that? they were
because we
not
performed the PCA analysis in order to verify which parameter play a crucial role in the toxicity.
Yeah, but with a PCA, you need to know, well, PCA just tells you where the variation
Yes.
is. It doesn't tell you what the.
And we only perform a correlation analysis.
So did you have something that was really clearly bad and something that was clearly good? And so it's sort of a polar ordination then, really,
Yes.
between those two poles. You sort of figure that it's probably one-dimensional in some sense,
sure, and
or can be reduced to one dimension.
distance from the waste is one dimensional as well, so it kind of makes sense. So,
Mhm.
So can you connect your laptop to that? screen?
Yes.
Do you like R or Python? What? Do you use R or Python at all?
I don't think I didn't understand anything we spoke.
Excel, he does.
Excel.
Yeah, it's Excel. Okay. How can I do that here?
There's a. Can you do that here?
There'll be something to connect. Do you have one of these?
I don't think he does. That's a very old fashioned.
No.
Do you
It's a
have?
VGA connector, isn't it?
Yeah.
Do you have USB-C? Because in my office I've got some wires for USB-C, HDMI. Just this HDMI. Oh, that's HDMI. Other side.
Yes.
Yeah, I decided I can't say the light is about so specified threshold, true positives, false negatives. And then with P boxes, really easy. So that was just the that's the proportion. So if you go by the version, just down to the example. But it's sort of
So how?
so we changed.
So we changed this selection from PC to VGA to HDMI. Probably?
Yeah.
Input no signal. Signal.
That recognize that.
I think so.
Yeah.
Cool. Yes.
Magical. So are we still sharing?
Yes.
I don't think we're sharing. Do you think we could possibly be sharing stuff?
Did you want us to stop the recording?
Whoever's in the video, we're recording.
And those guys still joining.
Well, Francis, can you still hear me?
Yeah.
The answer is no. Can we go back to PC for a minute? Francis, can you hear me?
Yeah, I can still hear you.
But you couldn't hear me just a moment before, right?
I could hear you. Yeah,
The whole time.
pretty much. Sometimes when people are quite far away, it's hard to make out. But we can stop sharing the recording if you like.
I guess we should do that. You were able to. We changed the display from the blue.
No, we won't be able to see that.
Okay. All right. So I guess we should adjourn then. Thanks very much, Francis. You can stop recording.
Okay, no problem.